In the early dawn of knowledge, when philosophers still walked barefoot across the stone courtyards of Athens, the ideas of space and time were anything but obvious to Aristotle. Space was something filled with objects, with motion, with what the eye could see. Time, by contrast, was abstract. No one could see time itself, only feel it pass. It was a measure of change, but by what standard, and against what frame, remained elusive. Motion, for Aristotle, was not the consequence of force. As we later came to believe, it was an expression of change from potential to actuality. An object fell because it desired to return to its natural place, and that place was at the center of the universe. It was not law, but intuition, a way of understanding the world through philosophical reasoning rather than measurement. And thus, he reasoned, a heavier object would fall faster than a lighter one, for it bore more of its intrinsic nature. But every line of reasoning is born from the age that gives it breath. Before clocks, before telescopes, before the very idea of speed as we now understand it, how could one measure acceleration? How could one distinguish constant motion from changing motion in that world? The idea that motion required a sustaining force made sense. A flying arrow, they believed, continued forward because the air behind it pushed it onward, a primitive notion of cause. From that, the logical conclusion followed: if nothing resisted motion, an object would move infinitely fast. This meant that a vacuum could not exist, for if there were empty space, then instant motion would follow. And if instantaneous motion existed, the world would unravel into absurdity. No force is infinite, therefore no motion should be. Space, then, must always be filled with something: air, water, fire, or a subtle, invisible substance, what some would later call the ether. Still, in the faint cracks of ancient knowledge, another idea was beginning to bloom, one not from Aristotle, but from less celebrated thinkers like Democritus, Epicurus, and later, Lucretius. They imagined a world made of indivisible particles, atoms moving through infinite emptiness. It was a vision too bold for its time. How could nothingness exist? How could there be a place devoid of anything, yet still be real? Aristotle rejected such a notion, not only because it contradicted his philosophical intuition, but because it lacked an explanation for motion. Why did these atoms move at all? What set them in motion? The atomists replied, the universe has always been in motion. But that was not enough for Aristotle, who believed knowledge must seek causes, not merely describe appearances. The world kept turning, and time marched on, in the hush of the Middle Ages. Small sparks began to glow in distant monasteries. Scholars like Philoponus, Hipparchus, and later, Roger Bacon and Robert Grosseteste began to question Aristotle. They experimented, measured, charted. They sought to unite the senses with numbers, intuition with proof. Through rough experimentation, they discovered that when two objects, one heavy, one light, were dropped, they fell at the same rate. This defied Aristotle's teachings, but matched what they observed. Slowly, they realized that what changed an object's motion wasn't its essence, but something external, a force. a new concept emerged: momentum. What we now call inertia. An object, once in motion, would continue moving unless acted upon. This marked a fundamental shift from believing that motion required continuous force to understanding that force caused change in motion, not motion itself. At that same time, a man named Leonardo da Vinci sat sketching observations of pendulums, flowing water, and falling objects. He lacked precision instruments but possessed something even more valuable: the eye of a careful observer. He began to notice that objects not only fall, they accelerate. From Leonardo to Galileo was a short step in time, but a long leap in thought. Galileo did not just observe. He measured. He experimented. Using inclined planes to slow falling objects, he measured intervals by the beat of his own pulse. And from this, he discovered that all objects in freefall accelerate at the same rate regardless of mass. A simple realization, but one that shattered thousands of years of Aristotelian thinking. Galileo also laid the foundation for measuring time, something no one before had truly done. He invented the pendulum clock, tuned the length of the cord to match regular intervals, and opened a door for physics, the door of law. But Galileo could not yet explain what kept planets circling the sun. He believed they moved in perfect circles because it was their nature, an echo of Aristotle still lingering. He overlooked or dismissed Kepler, who had already shown that planetary orbits were not circles, but ellipses. It was an omission, yet also a reminder: no one reaches the truth alone. Science advances by relay, not by solitude. Meanwhile, in France, René Descartes was contemplating existence in space. He believed only one thing was certain, I think. Therefore I am. From that premise, he imagined a mechanical universe, a cosmos without emptiness, like Aristotle. He believed that a vacuum was absurd. There could be no place where nothing existed. Every space must be filled. Every motion must result from contact. Every force must be a push or pull, not an action at a distance. He imagined the planets caught in invisible vortices, swirling cosmic whirlpools like pebbles carried in water. He could not accept that gravity might act without contact. That idea, he believed, defied reason. But that would later become the very thing he would confront in Newton. Christian Huygens, the Dutch physicist, continued the work of Galileo and Descartes. He calculated that objects in circular motion experienced inward acceleration, A equals v squared over r. He understood that circular motion was not natural, but required a force, the centripetal force, to keep an object from flying off. There was nothing remarkable about the apple itself. It fell, as all things fall. But to Newton, watching from the quiet of the orchard, the falling apple whispered of something deeper, a force that not only drew fruit to the ground, but might also hold the moon in its path. He began to wonder, what if the same invisible pull that brings objects downward also governs the dance of the planets? The thought was radical. Gravity, as Newton envisioned it, was not a push, not a vortex, not a mechanical shove from ether or air. It was a pull across emptiness, silent, instantaneous, reaching through the void. He did not explain how this force acted at a distance, only that it did, and in that silence, The world changed. With the publication of his Philosophia Naturalis Principia Mathematica, Newton laid out laws that would govern motion for centuries. His first law, an object in motion stays in motion unless acted upon. His second force equals mass times acceleration. And his third, for every action, an equal and opposite reaction. 3 lines that would become pillars of a new physics. 3 sentences that rewrote the language of nature. But it was his law of universal gravitation that unraveled the heavens. The same force that made the apple fall held the moon in orbit. The planets, too, obeyed this rule drawn toward the sun, yet never falling into it, always curving, always missing, always returning. Gravity was not a local curiosity, but a universal principle. No longer was the cosmos a place of separate spheres. Earth and sky were one continuum, bound by the same invisible hand. It was a triumph of unity. For the first time, the motions of stars and stones could be explained by a single idea. The universe became knowable, predictable, and for a moment, almost tame. Yet Newton's world was not without mystery. In his formulation, gravity acted across empty space. But what carried this force? What medium connected 2 masses if nothing lay between them? He offered no mechanism, only mathematics. To some, that was enough. To others, it was a wound in reason. Action at a distance remained a phantom real in calculation, unfathomable in substance. Still, the predictive power of Newton's laws silenced most objections. Comets that once seemed like divine messengers now followed curves that could be charted. Tides, once the domain of myth, could be forecast by the moon's position. The universe, once veiled in mystery, now yielded its rhythms to calculation. But as Newton's vision took hold, something subtler began to shift. The universe was no longer a stage for gods and souls, but a machine, a vast, clockwork mechanism wound at the beginning of time and ticking ever forward. In Newton's own words, God was necessary to set the system in motion, but once running, the laws required no further intervention. This idea spread quickly. Theologians resisted. Poets lamented. But the age of reason embraced it. The world became geometry, the sky, a set of equations, motion, mere arithmetic of matter. The cosmos seemed infinite, eternal, precise and disturbingly cold. Within this mechanical view, time became absolute. It ticked forward independently of events, like the regular beat of a perfect clock. Space, too, was fixed, a container in which objects moved. There was no curvature, no relativity, no distortion. Just a blank stage upon which forces played. This model brought incredible success. Engineers, astronomers, and navigators thrived under its certainty. Yet in that certainty, some began to feel something had been lost. The cosmos, once alive with intention, became mute. There was no why, only how. No meaning, only motion. Philosophy receded as equations advanced, and yet, not everyone accepted this silence. In the salons of Europe, in the monasteries of Italy, in the halls of Königsberg and Geneva, thinkers began to ask whether the universe was truly so rigid? If time was absolute, how could it be felt so differently? If space was fixed, why did perception twist its shapes? If nature was machine, where was the human soul? These questions waited. For though Newton's universe explained much, it could not explain everything. Light, for instance, refused to obey the tidy rules of matter. It bent, it interfered, it defied understanding. And gravity, still mysterious, remained instantaneous, a troubling fact for those who believed in finite cause and effect. Across Europe, curiosity grew restless. The certainty of Newton had been a comfort, but comfort breeds questions. If the universe was indeed a clock, then who had wound it? And why did some of its gears seem to stutter strange gears, like magnetism, light, or heat, that refused to click into the mechanical pattern? The nature of light became a riddle that unsettled even the most confident minds. Was it made of particles, as Newton himself believed, or was it a wave, like sound passing through air? Some experiments showed it bending around corners, interfering with itself like ripples on a pond. Others revealed that light could strike metal and knock loose tiny sparks, as if it were a bullet, not a wave. It behaved like both. And neither. It obeyed no single metaphor. And what of heat, that invisible fire which made metal expand and skin burn? Some called it a fluid, a substance named caloric that flowed from hot to cold. But this invisible substance could not be seen, trapped, or weighed. Others suggested that heat came from motion, the jostling of particles too small to see. If this was true, then everything solid and still was in fact dancing, trembling, alive beneath the surface. This view brought atoms back from philosophical exile. The ancient idea of tiny, indivisible particles, once dismissed as metaphysical fancy, now gained foothold in chemistry and physics alike. Invisible though they were, atoms explained much how substances combined, why gases expanded, why heat moved. The idea of a hidden world, a world of ceaseless, chaotic motion returned. Yet this invisible world raised strange dilemmas. If matter was made of atoms, what held them together? Why did some cling while others broke apart? And if everything moved endlessly, if time itself was stitched from motion, then what was motion through time? Could time change? Slow, bend? Not yet. Not in Newton's world. In his system, time flowed uniformly, unaffected by the observer, but a few daring thinkers began to see cracks. One of them was a patent clerk in Bern, a man who thought deeply about what it meant to move, to measure, to observe. Albert Einstein, with quiet precision, dismantled the foundation beneath absolute time. He asked a simple question: what if the speed of light was always the same? No matter how fast you moved, the answer was not so simple. If light never changed speed, then time must, and space must. The very fabric of the universe had to stretch, warp, and shift, depending on how one moved through it. With that, Newton's absolute space and time were undone. The universe was no longer a fixed grid. It was a woven cloth space, and time stitched together. Flexible, responsive, alive. Motion bent time. Gravity bent space. Mass became a measure of energy. Energy became fluid, shimmering, radiant. And gravity, that silent, unexplained pull, was no longer a force at all. It was a curve. Objects followed paths not because they were pulled, but because space itself was curved by mass. Planets orbited stars, not like marbles tugged by strings, but like dancers following the bend in a floor they could not see. It was a new language for an old story. Newton's apple still fell, but now it fell not because it was pulled, but because Earth had curved the stage beneath it. And light, too, bowed its head to gravity, bending its path near stars, revealing that even something thought massless could be swayed by the shape of space. Einstein had not replaced Newton, he had deepened him. Just as Newton once made Aristotle a special case of a larger truth, so Einstein made Newton's laws a shadow of a deeper structure, visible only at great speeds or near great masses. The clockwork cosmos had become a living geometry. Yet this geometry introduced its own enigmas. If space and time were relative, then what anchored reality? If the universe could bend, then could it twist into loops? Could time itself fold, allowing effects to precede causes? And if energy and matter were interchangeable, then what truly was substance? More unsettling still was what the new physics implied about the origin of the cosmos. If space could expand, then perhaps it had once been smaller, much smaller. Perhaps everything time, matter, energy had once been compressed into a single point, a beginning not just of things, but of being itself. The questions multiplied, the answers dissolved. Where Newton had drawn clean lines, Einstein sketched curves. Where Descartes saw machinery, Einstein saw elegance. The universe had not become less comprehensible, but it had become more mysterious. And mystery, once again, became the beginning of knowledge. The universe was no longer content to be seen. It now had to be imagined. In the dark silence between stars, space itself was growing, stretching not into something, but into itself. Galaxies receded, not because they moved through space, but because the very fabric of space was expanding between them. It was not an explosion through a medium, but a swelling of the medium itself, silent, unceasing, without center. What had once seemed eternal now had a beginning, a birth not from chaos, but from a singularity, a point of infinite density, infinite temperature, infinite curvature, a place where the known laws of physics broke apart. The so-called Big Bang was not an outward blast from a location, but a beginning of space and time alike. There was no before. There was no outside. The cosmos began not within something, but as something. And yet, what emerged from that singularity was not chaos, but order astonishing, fragile order. Forces separated, symmetries broke, particles formed. The blueprint of all that would ever exist was imprinted in those first moments. A fraction of a second after it began, the universe knew how to build stars, how to shape galaxies, how to breathe atoms into being. But this precision was unnerving. Why should the laws be so finely tuned? Why did gravity have just the right strength to allow galaxies, but not too strong to crush everything into black holes? Why was the expansion rate so delicately balanced that it did not halt or tear itself apart? Why were the constants of nature so exact, as if written with intent? Some saw providence. Others saw coincidence. Still others imagined multitudes a multiverse, infinite in variety, in which every possible configuration existed somewhere. In that vast landscape, our universe might not be special. It might simply be one of the few in which life could ask the question. But questions multiply in dark rooms. If space could expand, could it also tear? Could it form holes not just in space, but in the very order of cause and effect? General relativity permitted such structures, black holes, regions from which nothing, not even light, could escape. Not because something was pulling inward, but because the inward became all there was. The future, for anything crossing that boundary, pointed only deeper within, and what lay inside, no one knew. The equations collapsed. Space folded into space. Time folded into time. Mass became infinite, a singularity. Again, not at the beginning, but at the heart of unbeing. These were no longer philosophical riddles. They had become observable realities. Black holes were not just the fate of collapsed stars. They were real, detectable by their hunger, their shadows, their ripples in space-time. Einstein had not predicted them with joy, but with reluctance. He doubted they could form the universe. He hoped would not allow such monstrosities. But the universe allowed, and not just permitted, it required. Black holes formed not rarely, but often. They anchored galaxies. They shaped structure. They sculpted the cosmos like unseen hands, where Newton had given us force, and Einstein had given us curvature. Black holes gave us boundaries not physical, but conceptual. Inside their event horizons, all knowledge ended. No observer could report from within. No signal could return. In an age where physics had pried open the heavens, black holes were doors that remained shut, yet even they were not eternal. As Stephen Hawking later showed, black holes could radiate slowly, imperceptibly. They could evaporate. Through a quantum whisper at their edge, information could bleed away. And with it came a final paradox. If black holes destroyed information, then the laws of physics, which demanded reversibility, would fail. A tear appeared between the smooth curves of general relativity and the jittering probabilities of quantum mechanics. They were both true, and yet together, incomplete. The universe at large obeyed one rhythm. The universe of the small danced to another. Between them lay a silence no theory could cross. In that silence, some imagined strings vibrating filaments, infinitesimal, whose modes of vibration gave rise to mass, charge, force. Others imagined loops, granular time, or emergent space. But none could yet bridge the gap. The quest for a theory of everything had become the quest for a language the universe was still unwilling to speak. In the search for unity, the questions had only deepened. The more the universe revealed, the more elusive its heart became. What began as a desire to understand motion had led to a trembling awareness of mystery, not for lack of knowledge, but because knowledge had reached its edge. It was not just the cosmos that grew strange, but consciousness itself. If space could curve and time could stretch, then what of the observer in quantum theory? The act of observation changed the outcome. Particles existed in clouds of possibility until measured, as though reality itself required a witness. The boundary between world and mind blurred. Was consciousness merely an emergent function of matter? Or was it somehow woven into the very fabric of being? Some thought of the ancient Pythagoreans, who had believed that number and harmony governed all things. Others recalled the mystics, who spoke of the illusion of separateness, the unity behind form. Modern physics, in its own way, had circled back to such riddles, not in doctrine, but in implication. The vacuum, once dismissed by Aristotle as absurd, now seethed with energy a sea of fluctuations, particles appearing and vanishing in ghostly pairs. Emptiness was no longer empty, even nothing. It seemed, was something, and the universe itself, it still expands, accelerating with an energy no one can name. Dark energy. They call it not because it is understood, but because it is not. It pushes galaxies apart with a silent force, shaping the fate of everything, yet remaining beyond reach. Dark matter, too, passes unnoticed through all we see. It outweighs the visible stars, yet never shines. It holds galaxies together like scaffolding made of shadows. It neither emits nor absorbs light, but its gravity carves the shape of the cosmos. The familiar now floats in a sea of the unknown. All that we call atoms, stars, and light is but a sliver, a small island of the comprehensible amid a vast ocean of the hidden, and time, that old companion, may not be eternal. Some theories speak of a heat death, a future in which stars burn out, black holes fade, and all gradients dissolve. A universe of uniformity, cold and still, where nothing more can happen. Others imagine cycles, rebirths, bouncing cosmologies, where the end curls into a beginning. But even if the cosmos fades, the questions remain. Why do laws exist at all? Why should anything be ordered, measurable, or beautiful? Why is there something rather than nothing? No equation has answered that. No telescope has glimpsed its edge. We ask not because we are ignorant, but because we are aware. We seek not merely to explain, but to belong. The universe, in its vastness, does not speak, but it allows us to listen. From Aristotle's unmoved mover to Newton's universal law, from Einstein's curvature to the quantum veil, each step has drawn us deeper, not into certainty, but into awe. Perhaps the ultimate lesson is not how the universe works, but that we can ask at all. That in a corner of space, for a brief span of time, there are minds capable of wonder, and wonder, like gravity, pulls us forward.
From the dawn of consciousness, humanity has looked to the heavens, a canvas of infinite mystery, and whispered a question that resonates through the deepest corridors of our being. Are we alone for millennia? This was a query for poets, philosophers, and dreamers. But today, we stand at a remarkable threshold. Science, with its ever-sharpening tools and insatiable curiosity, is beginning to sketch the outlines of an answer. Are we, in this very epoch, about to find life far from Earth? The knowledge that thousands of worlds, the so-called exoplanets, orbit stars other than our own sun, is no longer the realm of science fiction. It is established astronomical fact. This realization, burgeoning over the past quarter century, has transformed our cosmic perspective. The grand question in the pale blue dot. The journey from the first tentative detections of these alien worlds, many of them initially appearing hostile, with conditions making life as we know it impossible, to the most recent discoveries of planets that bear a striking, tantalizing similarity to our own Earth, has been one of astonishingly rapid progress. This relentless advancement, achieved in just the last 25 years, fuels a profound and growing conviction within the scientific community that we are getting closer and closer, perhaps with each passing year, to the monumental discovery of an inhabited planet. Yet, the path to such a revelation is anything but simple. Discovering life somewhere within the unfathomable expanse of our galaxy will not be easy. Scientists, with unwavering determination, must confront and overcome major technological challenges, obstacles that test the very limits of human ingenuity and our current understanding of the cosmos. We are separated from other stars, even our nearest stellar neighbors, by gulfs of space so vast they beggar the imagination, distances measured not in miles or kilometers, but in light years, the very distance light itself, the fastest thing in the universe, travels in an entire year. And beyond these almost insurmountable physical barriers, a constellation of fundamental questions still remains unanswered. Questions that strike at the very heart of our quest. How did life, in all its intricate complexity, first ignite on our own planet? This precious, singular oasis of blue and green, in what kinds of diverse, perhaps even extreme, habitats could life appear and subsequently develop elsewhere, adapting and evolving under conditions that might seem utterly alien, perhaps even lethal, to us? Despite these daunting unknowns, astonishing projects, beacons of human ambition and scientific aspiration await us. Consider the James Webb Space Telescope, a marvel of engineering already peering into the depths of space, uniquely capable of studying the delicate atmospheres of distant planets in a direct search for the chemical signs of life. And looking to the near future, there is the ELT, the extremely large telescope, a gigantic ground-based observatory that promises to open an entirely new door, a fresh portal onto an unknown universe, potentially revealing vistas that will forever alter our perception of reality and our place within it. This, truly, is the time for the dream of a whole generation of astronomers, and indeed, the collective dream of all humankind to potentially come true. Because in the end, the search for other worlds, for other life, holds the extraordinary potential to provide a reply, perhaps even a definitive answer, to that most fundamental and enduring of all questions are we alone in the universe? To fully grasp the profound context of this search, to feel its emotional weight, we must cast our minds back, or rather, our gaze outward, to a singular, poignant moment in the year 1990. Shortly before abandoning our solar system forever, its primary mission of exploration largely complete, its instruments still faithfully reporting back across the void. The Voyager 1 space probe, a tiny, tenacious emissary of Earth, was commanded to look back one last time. From an almost inconceivable distance of 6,000 million kilometers, a vantage point from which our entire solar system would appear as little more than a collection of faint, insignificant sparks. It captured an image that would resonate through history, an image that would become an icon of the space age. Suspended on a single, delicate ray of sunlight, almost lost in the cosmic glare and the vastness of interplanetary space, the presence of a dim, almost imperceptible point of blue light could just be made out. That was Earth, our home, our world, everything we have ever known. The visionary astronomer Carl Sagan, who had passionately championed this act of cosmic self-reflection, famously called it the pale blue dot. Looking at that image, it is hard not to feel a profound sense of our own fragility, our preciousness, and indeed, our apparent isolation in the grand cosmic theater. And it compels us to ask, is it truly reasonable to think that this tiny, solitary dot, this mote of dust suspended in a sunbeam, is the only inhabited place in the entire, sprawling, almost unimaginably vast universe, as Carl Sagan himself so eloquently articulated? If the Earth is the only place where there is life, then it seems like an awful waste of space. If life, in all its tenacity, its adaptability, and its inherent drive towards complexity, has arisen on a planet such as ours, a world with its specific chemical composition, its particular orbital distance from its star, its unique geological and atmospheric history, then why, by what cosmic decree, could it not have also appeared, through similar processes of cosmic chemistry and Darwinian evolution, on other worlds, perhaps on countless other worlds, scattered like seeds across the galactic winds, each one a potential cradle for life? Just a few short decades ago, when we looked up at the night sky, our perception was limited. We simply saw stars, beautiful, twinkling points of light, certainly, each a distant sun, but essentially just that, individual stars. But today, our understanding, our cosmic imagination, has been irrevocably, wonderfully altered. When we now look at those same stars, those familiar constellations, we can, with solid scientific justification, imagine not just solitary points of light, but thousands upon thousands of planets orbiting them. We can envision a rich, intricate tapestry of planetary systems woven throughout the fabric of our galaxy, a galaxy itself just one among billions. And these planets, we now understand, have been formed in the same fundamental way as our own solar system, coalescing over eons from vast, swirling disks of gas and dust surrounding their nascent, youthful stars, a universal, almost inevitable, process of cosmic creation. To truly begin to grasp the sheer potential for life elsewhere, one must first attempt to confront the staggering, mind-boggling scale of our universe. how many stars are there, just within our own Milky Way galaxy, let alone in the countless other galaxies that speckle the observable cosmos like luminous grains of sand on an infinite shore. The number is, quite frankly, very, very big, a figure that defies easy comprehension and dwarfs any terrestrial analogy. Sometimes, in an attempt to make it relatable, we think that the number of grains of sand on all the beaches and deserts of our entire Earth might be a comparable figure, but it's not. The reality is even more immense. Current astronomical estimates suggest that there are about 10 billion stars in the observable universe. That means, if you could somehow count them one by one, there would be roughly 1,000 times more stars in the heavens than there are individual grains of sand on our entire planet. The sheer statistical weight of this number is almost overwhelming. Equations, signals, and enduring paradoxes. Confronted with such an astronomical number of stars, each a potential sun with its own retinue of orbiting worlds, even if life, and particularly intelligent, communicative life, were an exceedingly rare cosmic accident, a statistical improbability of the highest order, the sheer number of worlds on which it could have arisen remains utterly, profoundly enormous. This fundamental realization was understood with striking clarity by the North American astronomer Frank Drake. As early as 1961, Drake put forward his now famous equation, a conceptual framework designed not so much to yield a precise number, but rather to organize our thinking, to systematically break down the grand question of how many communicative civilizations might exist in our Milky Way galaxy into a series of more manageable, albeit still hugely challenging, probabilistic questions. The Drake equation, elegant in its simplicity, attempts to measure the number of civilizations in our Milky Way capable of, and perhaps interested in, communicating with others. It multiplies together several key factors, the average rate of star formation in our galaxy, the fraction of those stars that have planets, the average number of planets that can potentially support life per star that has planets, the fraction of those potentially habitable planets on which life actually arises, the fraction of life-bearing planets on which intelligent life evolves, the fraction of civilizations with intelligent life that develop technology capable of releasing detectable signs of their existence into space, and finally, the length of time such technologically advanced civilizations might release those detectable signals. It is, in all likelihood, an equation whose precise solution will elude us for a very long time, perhaps forever, because we are, at present, largely unaware of the true values of most of its variables. And each of those variables, each term in that chain of probabilities, itself brings up a cascade of new, complex, and fascinating questions, each one a vibrant line of research in current astronomy and astrobiology. As one scientist deeply involved in this multifaceted research has noted, I think what is interesting is it depends on how many stars are in the universe and how many new stars form every year, how many planets they typically have, if they have any planets, how many of those planets are truly habitable. If they are habitable, do they already have life, or perhaps did life arise and then disappear? Do they have intelligent life? Is this intelligent life anything like ours? Will they communicate as we do, or in ways we can't even imagine? Each of these questions, as mentioned, represents a significant and active line of research in contemporary astronomy. We don't yet know with certainty how many stars form in the universe, at what precise rate, for example. So, imagine, if even these fundamental astronomical parameters are still subjects of ongoing investigation, how could we possibly perform the full Drake calculation with any high degree of confidence in the final result? Yet, the spirit of the Drake equation, its powerful impetus to systematically explore the probabilities and to identify the key unknowns, continues to inspire and to guide the search. And so, since the 1970s, driven by the conviction, or at least by the fervent hope, of the existence of other intelligent civilizations within our galaxy, the SETI projects, the search for extraterrestrial intelligence, have diligently, patiently trolled the stars. These projects have employed powerful radio telescopes to listen intently, scanning the cosmic airwaves, sifting through the natural background noise of the universe in search of any faint, artificial signals, any whispers that might betray an extraterrestrial, technological origin. We are, of course, designing these searches based primarily on what we ourselves do, on our own current technological footprint. Here on Earth, we communicate over vast distances, predominantly using radio waves, and indeed, from our current perspective, this remains the most practical and detectable way for signals from a human-like civilization to be perceived from outer space. Over the recent decades of this patient, often thankless, listening, some hopeful, tantalizing signs have occasionally been found, fleeting, unexplained anomalies in the cosmic static that briefly raise pulses and ignite speculation. But alas, upon closer scrutiny and further investigation, none of them have ultimately turned out to be a verifiable greeting from the vastness of interstellar space. One must then ask, were the pioneers of the SETI search, in their early, unbridled enthusiasm, perhaps a shade too optimistic? Did they underestimate the profound silence of the universe, or the sheer, daunting difficulty of the task they had set for themselves? Perhaps a profound shift in our very understanding of the universe's scale, a pivotal astronomical discovery that occurred decades before the first formal SETI projects even began, contributed both to the initial optimism and, subsequently, to a more sober, more measured realization of the immense challenge involved. In the year 1924, the American astronomer Edwin Hubble, through meticulous observation using the powerful telescopes of his era and groundbreaking analytical insight, confirmed a revolutionary idea. He demonstrated conclusively that the Andromeda Nebula, long thought by many to be a swirling cloud of gas and dust located within the confines of our own Milky Way galaxy, was in fact not a nebula at all. It was an entirely separate galaxy, a vast, majestic island universe in its own right, containing billions of its own stars, and lying millions of light years beyond the outermost fringes of our own galactic home. In that singular moment of discovery, the universe, as humanity understood it, had suddenly, dramatically, become effectively infinite, or at least vastly, unimaginably larger than anyone had previously dared to conceive. Until that pivotal discovery, scarcely a century ago, almost everybody, scientist and layperson alike, generally thought that our galaxy, the the Milky Way, was the universe, the entirety of creation, the sum total of all that existed. Now, we know that those little, fuzzy, indistinct dots that appear like faint, ethereal stars through our most powerful telescopes are, in reality, other galaxies, each a colossal stellar system, each containing its own billions, perhaps even trillions of stars. Our perspective has changed so profoundly, so rapidly, that our minds, our everyday intuitions, often struggle to truly comprehend the idea of such immensity, such near infinity. We can certainly manipulate the concept mathematically. We can write down the equations that describe it. But our brains, which evolved on the savannas of Africa to deal with more immediate, more terrestrial concerns like finding food and avoiding predators, did not evolve to intuitively understand this kind of mind-bending cosmic scale. Then, the universe is effectively infinite, or at least so unimaginably vast and sprawling, and is teeming with galaxies, each of which contains thousands of millions, or even billions of stars. It seems almost logical, almost inescapable, to think that other intelligent civilizations, perhaps many like our own, or perhaps wildly different, must surely exist out there somewhere. Why then, given this apparent logical imperative, this statistical probability, have we not yet had any definitive news, any unambiguous signal, any clear indication of contact from any of our potential galactic neighbors? This is the very crux of the profound and unsettling question that the brilliant Italian-American physicist Enrico Fermi is said to have famously, almost casually, posed during a lunchtime conversation with colleagues at Los Alamos in 1950. A question now enshrined in the annals of scientific thought as the Fermi paradox, where are they? The implication of Fermi's simple yet profound question is clear and deeply challenging given the immense age and staggering size of the universe, and the presumed likelihood of life arising given enough suitable worlds and enough time. We should, by now, have seen or detected some incontrovertible evidence, some clear signals of an alien civilization. Yet, despite decades of looking and listening, we haven't. There are, of course, numerous possible, and often quite unsettling, reasons for this apparent great silence, one stark, and to some, chilling. Possibility is that there simply aren't any other civilizations in our galaxy capable of, or perhaps interested in, communicating. Perhaps we are truly, profoundly alone, at least in this particular cosmic neighborhood, at this particular moment in cosmic time. Another, perhaps more nuanced, possibility is that we are not in the same space and time frame. Civilizations may rise and fall like ephemeral mayflies on a vast cosmic timescale, their windows of technological capability and interstellar communication too brief, too fleeting, to overlap with our own relatively recent emergence as a signal-producing species. Life, as we understand its history on Earth, arose on our planet over 3,500 million years ago, a slow, painstaking, and often precarious evolutionary journey from simple microbes to the complex biosphere we see today. Yet, we, as a species capable of deliberately broadcasting our presence into the vastness of space through radio waves, have only been giving off potentially detectable signals for a mere 100 years or so, an infinitesimal blink of an eye, in the grand sweep of cosmic time. What, then, are the realistic possibilities of our brief period of detectability coinciding with that of another civilization, somewhere else in our vast galaxy, especially when separated by immense gulfs of both space and time? And if we add to this temporal difficulty the almost incomprehensible distances that separate us from even the nearest other worlds that might harbor life, the challenges become even more profoundly complicated. As one astronomer involved in these contemplative calculations explained, if we have a civilization that is, say, 20,000 light years away, even if we were to detect their signal today, it would take a full 20,000 years for our reply, traveling at the speed of light to reach them. And then, if they were to answer back immediately, it would be another 20,000 years for their response to traverse the interstellar void and arrive back at Earth. So, that's a 40,000-year round trip for a single exchange of messages. This is not really a very productive or practical dialogue that we could realistically have. Our galaxy, the Milky Way, is roughly 100,000 light years in dimension, from one spiral arm to the far-flung other. That's a truly huge place, an almost unimaginably vast arena, and the fundamental speed limit of light, as dictated by Einstein's theories, imposes an absolute constraint on any attempt at interstellar conversation or rapid travel. The question, therefore, remains suspended in the cosmic ether, poignant, tantalizing, and profoundly unanswered. Do we really know, with any certainty, whether there's another civilization out there? Maybe there has been, long ago, their magnificent empires now crumbled to dust, their guiding lights now faded into the long night, their signals long since passed us by, unheard and unrecorded. Maybe there will be, far in the distant future, long after our own sun has exhausted its nuclear fires and our own civilization, perhaps, is no more. Or maybe, just maybe, there is intelligent life out there right now, coexisting with us in this vast galactic ecosystem. But they are too far away for their faint whispers to reach us, or perhaps too different in their nature or their technology for us to recognize their signals. Or maybe they are simply too quiet, content in their own cosmic solitude, for us to perceive their presence. For the time being, despite all our sophisticated searching and all our intricate theories, we just don't know. We do not know if we are alone or not. But even in this profound state of unknowing, even as we grapple with these immense cosmic uncertainties and the weight of these philosophical questions, we have, in the process of our search, discovered so many other amazing, breathtaking things about the universe itself, its intricate structure, its violent and beautiful history, the elegant physical laws that govern its operation, from the smallest subatomic particle to the grandest supercluster of galaxies. And it is this intrinsic journey of discovery, this relentless, curiosity-driven pursuit of knowledge, that continues to propel us forward as we delve ever deeper into the sophisticated methods and the landmark milestones that are, step by painstaking step, bringing us ever closer to a potential answer, an answer that could, in a single moment, change everything we thought we knew about ourselves and our place in the cosmos. The quest for understanding is, in itself, a profound testament to the very life we seek to find elsewhere. Inquisitive, persistent, and forever reaching for the distant stars. The Astronomer's Toolkit, Deciphering Cosmic Light. Welcome back to our ongoing exploration of the universe and our search for companionship among the stars in our profound quest to find life beyond the familiar confines of Earth, to seek an answer to that age-old, resonant question of whether we are solitary beings adrift in an immense cosmic ocean or part of a vast, interconnected web of existence. The very first, indispensable step is the discovery and characterization of other worlds. Before we can even begin to dream of detecting the subtle chemical signatures of life, or to contemplate the almost unimaginable implications of potential contact, we must first locate these distant celestial bodies, these exoplanets, faithfully orbiting stars far beyond our own familiar sun. But how? One might reasonably wonder. Do astronomers manage to study these remote objects that are light years away, often utterly invisible to the unassisted human eye, and forever beyond our current physical reach? The field of astronomy, particularly when it ventures into the challenging realm of extrasolar planets, inherently involves a major, almost defining difficulty we cannot, as scientists in many other disciplines routinely might, bring our subject of study, a distant star, a swirling nebula, or an elusive exoplanet, into the controlled environment of the laboratory for meticulous, hands-on examination. Often, we cannot even directly see the specific object of our intense scientific scrutiny, especially when that object is a small, dim planet, lost in the overwhelming glare of its parent star. How then, given these profound and inherent limitations, has it been possible for humanity to accumulate such a vast, intricate, and ever-expanding body of knowledge about the cosmos and its myriad, diverse inhabitants? The key, the fundamental secret to unlocking the universe's deepest mysteries from such immense distances, lies in patient, meticulous, and often incredibly ingenious observation. It relies on making clever and insightful use of the opportunities that the universe itself, governed by its immutable and universally applicable physical laws, graciously, if sometimes cryptically, offers us. Every single object in the universe, from the smallest, almost infinitesimal dust grain, drifting in the interstellar void, to the most massive, incandescent star blazing in the galactic core, from a still-forming, nascent planet coalescing in a protoplanetary disk to an entire, majestic galaxy containing billions of stars, emits energy. This energy, the universe's silent language, very often takes the form of electromagnetic radiation. This is a broad, continuous spectrum of waves that encompasses everything from the long, gentle undulations of radio waves and microwaves, through the warmth of infrared radiation and the familiar colors of visible light, to the energetic, high-frequency realms of ultraviolet light, X-rays, and the intensely powerful gamma rays. The specific characteristics of this emitted radiation, its overall intensity, its distribution across the different wavelengths of the spectrum, the presence of specific bright emission lines or dark absorption lines, depend critically and informatively on the temperature, the chemical composition, the density, and the physical state of the emitting object. Light, in its most fundamental physical sense, is a form of energy and one of the most powerful and versatile astronomical methods ever devised. A technique known as spectroscopy allows us to dissect this incoming cosmic energy with remarkable precision. Using specialized devices like diffraction gratings or prisms, coupled with sophisticated detectors and instruments, spectroscopy can split the faint, ancient light arriving from a distant celestial body into its individual portions, its constituent wavelengths or colors, much like a simple prism famously creates a rainbow from sunlight by dispersing its different wavelengths. And this collection of dispersed light, this unique, characteristic fingerprint of brightness versus wavelength, we call a spectrum. We humans, with our biologically evolved eyes, can only perceive a very tiny, almost insignificant sliver of this vast electromagnetic spectrum, the narrow band of wavelengths we call visible light. But the universe, in its full, magnificent glory, reveals its deepest secrets to us across the entire breadth of the electromagnetic spectrum, a vast, rich canvas of information patiently waiting to be deciphered by our instruments and our intellect. As one expert in the intricate field of astrophysical instrumentation explains, a spectrum that we can see with our own eyes, the familiar rainbow, is just a very, very tiny part of the possible range of wavelengths that are emitted by all the different kinds of objects in the universe. So, of course, different objects emit differently. Some of them, like cool dust clouds or young planets, emit most of their radiation in the infrared part of the spectrum. Hotter objects, like stars, might peak in the optical or even the ultraviolet. Extremely energetic phenomena, like accretion disks around black holes or supernova remnants, can blaze in X-rays or gamma rays. And analyzing these spectra, understanding these different emissions, tells us what are the inner makings of stars and planets, what is the detailed structure of galaxies, and indeed, what is the overall architecture and evolution of the universe on its largest scales. This remarkable ability to read the light, to decode its subtle messages imprinted by atoms and molecules light years away, is the absolute cornerstone of modern astrophysics. It allows us to determine the surface temperature of a distant star with surprising accuracy, to identify the specific chemical elements present in its atmosphere, to measure its precise speed towards or away from us using the Doppler effect, and even indirectly but powerfully, to infer the presence and properties of unseen companions, such as exoplanets, orbiting around it. But to capture this incredibly faint, unimaginably ancient light that has often traveled for thousands, millions, or even billions of years across the desolate vacuum of space to finally reach our telescopes, astronomy not only requires these highly sophisticated instruments capable of looking further and with greater analytical power than the unaided naked eye, it also, critically and fundamentally, needs specific places on Earth that are blessed with exceptionally good, pristine conditions for astronomical observation. These are typically remote, often inhospitable, high-altitude locations, deliberately situated far from the pervasive glow of artificial light, pollution emanating from our cities and towns, places where the overlying atmosphere is as thin, as stable, and as transparent as possible. And, of course, it requires telescopes, great, modern temples of science, marvels of engineering, capable of gathering vast amounts of this precious cosmic light, collecting the individual photons that are the fundamental messengers from the distant universe. One of the most impressive and productive of these modern ground-based observatories is the Gran Telescopio Canarias, often referred to by its acronym GTC. This magnificent instrument is perched high atop an extinct volcano on the island of La Palma, one of Spain's Canary Islands, floating in the Atlantic Ocean off the coast of Africa. Romano Corradi, the director of the GTC, elaborates on the essential, almost non-negotiable, requirements for such a world-class astronomical facility. We astronomers, we absolutely need that there are no clouds, or as few as possible. And here on the mountains of La Palma, for about 75% of the time, there are no clouds. That's a very high fraction of usable nights. Also, there are two other very important things we have here. We have the benefit of the trade winds, which are very good because they create a very stable, laminar flow of air over the mountaintop, meaning the atmosphere is very clean and the turbulence is minimized. This allows us to take very sharp, clear images of the universe, and, crucially, we are on a relatively small island, which is protected by law against excessive light pollution, helping to keep our night skies dark. Here, amidst the stark, almost lunar beauty of the volcanic landscape, under some of the clearest and darkest night skies on the entire planet, astronomers engage in their nightly vigil, a patient and meticulous dance with the cosmos. Their primary task, as Director Corradi succinctly puts it, is to collect the light that comes from the stars and other celestial objects, and then to either get images of those objects or, more often, to analyze that light in detail using our various instruments. To achieve this, they employ a diverse and sophisticated array of scientific instruments, some of which are designed to see the kind of light that our human eyes can perceive, the optical spectrum, while other, equally important, instruments are able to detect light that our eyes are completely blind to, such as the longer wavelengths of infrared light. Infrared astronomy is particularly crucial because it can reveal cooler objects like forming stars and planets, or allow us to peer through vast, obscuring clouds of interstellar dust that are opaque to visible light. The enormous primary mirrors of these large telescopes, which are not made of a single piece of glass, but are typically composed of many smaller, precisely shaped, hexagonal segments fitted together like a giant mosaic, act as colossal light buckets. They allow astronomers to gather the incredibly dim, almost ghostly particles of light, the individual photons, that finally reach us after their unimaginably long journeys of thousands, millions, or even billions of years, carrying with them faint, ancient tales from distant stars, nebulae, and even more distant galaxies, relics from the universe's deep past. The Gran Telescopio Canarias, the GTC, is currently the largest single-aperture optical telescope in the world. Its segmented primary mirror, a marvel of optomechanical engineering, has a collective light-gathering diameter equivalent to a colossal 10 meters. This immense light-gathering power, this ability to collect as many photons as possible, is absolutely crucial for many cutting-edge areas of modern astronomy. But it is especially vital for the incredibly challenging hunt for exoplanets, which are often vanishingly faint compared to the overwhelming glare of their host stars. and for studying their even fainter atmospheric signatures. It's worth noting, as an interesting technical detail, that these giant modern telescopes don't use massive lenses, like smaller, amateur telescopes or traditional spyglasses might. It's far easier, both mechanically and optically, to build, support, and maintain the precise shape of extremely large mirrors than it would be to create equally massive, perfectly formed, and optically flawless lenses. The profound idea that there might be other worlds beyond the familiar confines of our own solar system, planets orbiting other suns, is not, in itself, a particularly new or modern one. Down through the centuries, from antiquity through the Renaissance and beyond, great thinkers, insightful philosophers, and imaginative writers, figures such as Epicurus in ancient Greece, or the tragically fated Renaissance scholar Giordano Bruno, hazarded the well-reasoned opinion, based on philosophical analogy and a belief in the uniformity of nature, that there simply must be planets orbiting other stars. It was a beautiful, intellectually compelling, and deeply resonant idea, but for a very, very long time, it remained purely in the realm of abstract speculation, a fascinating concept far beyond the reach of any possible empirical verification or scientific proof. It was not, however, until the relatively recent past, specifically the 1990s, that the relentless, accelerating development of technology, particularly the advent of highly sensitive electronic light detectors like CCDs, the precision engineering of spectrographs, and the rapidly increasing power of computers for data analysis, finally allowed for the actual, unambiguous detection of these long-suspected extrasolar planets. It serves as a stark and humbling reminder of just how rapidly our scientific capabilities have advanced in a very short span of human history until just a couple of decades ago. The 8 recognized planets of our own solar system were the only planets whose existence we knew with absolute certainty in the entire vast universe. The fundamental question that occupies so many thoughtful minds, the profound inquiry concerning the ultimate origin of life itself and, by extension, whether that precious spark of existence has ignited elsewhere in the cosmos, hinges critically and inescapably on this first crucial step, the detection of other potential abodes for life. Before you can even begin to contemplate the possibility of extraterrestrial life, the very first thing you need to have, the foundational requirement, is a place where life can plausibly exist. We astronomers, or at least a significant number of us, had always suspected, based on our understanding of stellar and planetary formation theories, that there should be other planets out there. Indeed, from a purely theoretical point of view, the formation of planets looked like a natural, almost inevitable, byproduct of the complex physical processes involved in the birth of stars themselves, from collapsing clouds of interstellar gas and dust. The historic and picturesque city of Geneva, Switzerland, renowned globally for its long tradition of precision watchmaking and its prominent role in international diplomacy and finance, was, perhaps somewhat unexpectedly, to become the setting for this first successful, scientifically validated search for worlds beyond our solar system. In the early to mid-1990s, several highly skilled and intensely competitive research teams around the globe were deeply involved in this exhilarating, high-stakes scientific race, each team pushing the absolute limits of their sophisticated instruments and their intricate analytical techniques, the first to definitively cross the finish line, the team to proudly announce the first confirmed detection of a planet orbiting a sun-like star outside of our solar system, was the distinguished group led by the Swiss astronomers Didier Queloz and Michel Maillot. In the landmark year of 1995, the world of science, and indeed the wider world, was formally introduced to a new celestial citizen, the exoplanet designated 51 Pegasi b. It was a truly watershed moment in the history of astronomy, a discovery that would forever and irrevocably change our human view of the cosmos and our potential place within it. This monumental achievement would, many years later, deservedly earn its discoverers, Mayer and Queloz, the Nobel Prize in Physics. Didier Queloz, reflecting on that pivotal and exhilarating time in his scientific career, remarked with characteristic modesty and insight, "We had just got to know 51 Pegasi b. We just arrived at the right time, a moment in history where the available technology, the precision of our instruments, finally allowed us to give a genuine scientific answer, a data-driven response to this very old, very profound philosophical question. So, I feel myself very fortunate, very happy, to have just arrived at this good moment in scientific history in order to be part of the team that discovered the first exoplanet around a sun-like star." The ingenious and highly sensitive method that Michel Mayer and Didier Queloz had so successfully and groundbreakingly employed is known to astronomers as the radial velocity technique. It is sometimes more colloquially, and perhaps more intuitively, referred to as the wobble method. By meticulously applying this technique, they were able to detect the incredibly slight, yet periodic, movements of the star 51. Pegasi, subtle shifts in its position that were being caused by the persistent gravitational tug of an unseen, orbiting planetary companion, as an exoplanet circles its host star, its own gravity, though much weaker than the stars, inexorably causes the star to move in a tiny corresponding orbit of its own. It's a delicate, gravitational dance performed by the star and its planet around their common center of mass, a point often located very close to, or even within, the star itself if the planet is much less massive. When we, as observers on Earth, carefully measure the radial velocity of distant stars, that is, their speed directly along our line of sight, either towards us or away from us, it's all about our instrumental ability to measure these very, very tiny, almost infinitesimal variations in that stellar velocity over time. This small periodic stellar movement, this subtle wobble, can be precisely measured because the waves of light in the spectrum emitted by the star systematically vary due to the well-understood physical principle known as the Doppler effect. This is exactly the same effect that causes the noticeable change in pitch of an ambulance siren as it speeds past you as the ambulance moves towards you. The sound waves it emits are compressed, leading to a shorter wavelength and thus a higher perceived pitch. Conversely, as it moves away from you, the sound waves are stretched out, resulting in a longer wavelength and a lower perceived pitch. Similarly, as a star, influenced by an orbiting planet, wobbles slightly towards us in its tiny orbit, the light waves it emits are minutely compressed, causing its entire spectrum to shift very slightly towards the blue end of the rainbow. And as it wobbles away from us, its light waves are correspondingly stretched shifting its spectrum towards the red end. The star itself might be majestically careening through the vastness of the galaxy at truly enormous speeds, perhaps hundreds of thousands of kilometers per hour relative to our solar system. However, the incredibly subtle effect that astronomers are attempting to measure, the tiny periodic wobble induced by an orbiting planet, is often at the level of mere meters per second in velocity, or even less. To put this extraordinary challenge into a more familiar perspective, consider the gravitational pull of Jupiter, by far the largest and most massive planet in our own solar system. Jupiter's presence causes our Sun to wobble at a speed of approximately 12 meters per second, a speed roughly equivalent to a fast human sprint. The first generation of highly specialized astronomical instruments, such as the LOD spectrograph used by Mayer and Queloz at the Haute-Provence Observatory in France, were just sensitive enough, just precise enough, to reliably get to that level of detection capability. And so, it was entirely natural, and indeed expected, that the very first exoplanets they successfully detected using this pioneering technique were predominantly big, massive planets, gas giants comparable in size or mass to Jupiter, orbiting relatively close to their host stars, as these would produce the largest and most easily discernible stellar wobbles. New windows on worlds, transits, images, and the red frontier. Welcome back. The era of exoplanet discovery, ignited by the detection of 51 Pegasi b and its hot Jupiter brethren, was in full swing. The radial velocity method had proven its power, but the universe, it seemed, had an even greater diversity of worlds to reveal, and scientists were eager for new techniques to uncover them, especially those smaller, potentially rockier planets that might offer more clement conditions for life. While the teams perfecting the radial velocity technique continued their meticulous work, other astronomers were pursuing a different path, one that relied not on a star's wobble, but on its wink. This was the transit method, and Hans Dieg was among its early proponents, recalling his entry into this nascent field. In 1994, I was approached by a colleague, Lawrence Doyle, who proposed an experiment to search for exoplanets. So we started the first observational search for exoplanets with the method of transits. This elegant technique is based on the study of minuscule changes in a star's brightness. One doesn't observe the planet directly. Instead, the focus is on the star's light. If a planet's orbit happens to be aligned edge-on from our perspective on Earth, it will periodically pass in front of its star, an event astronomers call a transit. During these few hours, the planet will block a tiny fraction of the starlight, causing the star to appear slightly fainter. To confirm a planet, this dimming must be periodic, repeating reliably, and at least 3 such events are typically required to rule out other stellar phenomena. The primary limitation, however, is this precise geometric alignment. Only a small fraction of planetary systems will be oriented in just the right way for us to observe transits. Thus, the strategy has always been to observe many stars simultaneously, thousands, even hundreds of thousands, hoping that chance will align a few of them perfectly. While Dieg's early efforts were pioneering, the transit method truly came into its own with the launch of NASA's Kepler Space Telescope in 2009. Kepler was a dedicated planet-hunting observatory, staring unblinkingly at a single patch of sky for years, monitoring the brightness of over 150,000 stars with unprecedented precision. Kepler revolutionized the search, confirming hundreds of new exoplanets and identifying thousands of candidates. It made planetary transits the most successful detection method to date, revealing the first systems with multiple planets transiting the same star and amplifying enormously the sheer variety of planetary systems known to exist. It found many unusual things, truly a true revolution in our understanding of extrasolar planets. A few years before Kepler's launch, in 2003, another significant advancement occurred with the installation of HARPS, the High-Accuracy Radial Velocity Planet Searcher, an instrument of exceptional stability and precision, capable of detecting stellar movements as slight as 1 meter per second. HARPS, while still far from the 9 centimeters per second wobble Earth induces in our Sun, opened the door to discovering smaller and smaller planets. As astronomers using HARPS discovered, if you look in our solar system, there is nothing between planets like the Earth and planets like Uranus or Neptune. But in all or most of the other solar systems, there are what we call super-Earths or mini-Neptunes, meaning planets that are probably mainly rocky, but with masses between 2 and 10 times the mass of the Earth. These worlds, unknown in our solar system, appear to be ubiquitous in the universe. Then, in 2004, a new name appeared to mark a historic moment: 2M1207b, the first extrasolar planet to be directly imaged. Capturing a direct visual of an exoplanet is incredibly difficult. Planets are not very bright objects, and their host stars are overwhelmingly brilliant. The challenge is akin to trying to spot a tiny firefly perched on the bulb of a blindingly bright lighthouse from a distance of about 5,000 kilometers. To even attempt this, astronomers must develop specific techniques and instruments to remove or suppress the star's light, allowing the faint image of the planet to emerge. Furthermore, Earth's turbulent atmosphere distorts incoming starlight, blurring an already faint image. To overcome this, a complex technique known as adaptive optics is employed. This is a control system where sensors detect the optical distortions from the atmosphere as they occur, and this information is then fed back in real time to a deformable mirror, which adjusts its shape about 1,000 times a second to correct for these disturbances, producing a much sharper image. The advantage of a direct image is the wealth of information it can provide: the planet's size, the composition of its atmosphere, details of its orbit, and its temperature. The disadvantage is that, currently, we can only obtain direct images of young, still warm planets, or those which are a very long way from their star, where the contrast issue is less severe. For most exoplanets, we must continue to rely on indirect methods like radial velocity, which gives us the planet's minimum mass, or the transit method, from which we can ascertain its size. If we are fortunate enough to have both measurements for the same planet, we can compute its mean density, which tells us a lot about whether it is primarily rocky, like Earth, or gaseous, like Jupiter. Combining transit and radial velocity data is therefore key to truly getting to know the fundamental characteristics of a planet, although this is not always possible. Proxima b, the nearest known exoplanet, was detected using the radial velocity method. However, as its orbit is not aligned with Earth for us to observe a transit, we have not yet been able to determine its size. Chance has a significant role to play in transit detections. With radial velocity, on the other hand, success is virtually assured, provided the planet is not at too great a distance from us and is massive enough to produce a detectable signal. For this reason, new search projects are increasingly concentrating on the stars closest to our Sun. In this solar vicinity, we are seeing that the frequency, the occurrence rate of planets, is very large. At least 50% of these nearby stars have planets, and this includes even small ones. If we extrapolate this a bit, it means that, on average, one star out of every 2 in the galaxy likely has at least one planet. Considering there are hundreds of billions of stars in our galaxy, this implies there are at least hundreds of billions of planets, a truly staggering number of potential abodes for life. Not all solar systems, however, are ideal for life as we currently understand it. A wide diversity of stars exists, classified mainly by their temperature and mass. If we have to choose a good place to live, it is probably best to avoid the hottest and most massive stars in the universe. These celestial behemoths have extremely short lifetimes, often consuming their nuclear fuel and dying violently in a supernova explosion within just a few million years. The higher mass stars are much less likely to form stable planets, and even if they do, their brief and tumultuous existence hardly provides the eons of stability thought necessary for life to arise and evolve. In contrast, yellow dwarfs such as our Sun, which are G-type stars, fuse hydrogen much more slowly, enjoying lifespans of around 10,000 million years. This vast timescale would, in theory, allow ample opportunity for life to develop. Originally, astronomers were primarily trying to look for exoplanets around these G-type stars, because our Sun is a G-type star, and, of course, what you really always want to find is an Earth around a star which is very similar to the Sun. In principle, what we are after is a twin of ourself. Yellow dwarfs such as our Sun certainly provide suitable conditions for the development of life, but finding a true twin planet like the Earth orbiting one of them, a planet that is both small in size and situated at just the right distance from its star, is, for the moment, a very difficult task. We have found planets very close to their stars, and planets relatively far away from their stars, because in those situations, the overwhelming light of the star is not bothering us so much, or the planetary signal is easier to disentangle. But it just so happens, through a quirk of observational physics, that an Earth-like planet, which is at just the right distance from its star, so it's not too hot nor too cold, are the most difficult to find. It's bad luck, observationally speaking, but that's physics. Since the first detections and the continuous improvement of our instrumentation, astronomers have been relentlessly trying to get to these small planets at a good distance from their star, where liquid water could potentially exist at the surface of the planet. That's what we call habitable, in a very naive but operationally useful way. We do not yet know precisely how life first came about on Earth, but we do know that it would have been impossible without the presence of liquid water. The search for another Earth is therefore inextricably conditioned by the presence of water, specifically liquid water, within what astronomers call the habitable zone. The habitable zone is a concept that is in constant redefinition, and its extent depends on several different factors: how much light the host star emits, the wavelength distribution of this light, the surface gravity of the planet, the specific components of that atmosphere, and also the sheer abundance of water on the planet. A planet situated within this calculated habitable zone could still have a surface temperature very different from what might be naively expected, depending on whether it absorbs or reflects the radiation from its star. A very important factor here is the presence of an atmosphere. The mean surface temperature on the Earth is about 15 degrees Celsius, but it is estimated that if there were no atmosphere, if Earth were a bare rock, its average temperature would drop to about minus 20 degrees Celsius. This crucial increase in temperature is produced by the greenhouse effect. An extreme example of this is the planet Venus, where runaway greenhouse gases have formed such a dense atmosphere that the surface pressure is 90 times that of Earth. It is for this reason that its surface temperature has increased by over 500 degrees Celsius, making it hotter than Mercury. On the other hand, there's a property called albedo, which describes what fraction of the incoming starlight is reflected by the surface of the planet. This depends on the composition of the planet and also in which state these components are. This delicate equilibrium between the warming greenhouse effect and the cooling influence of albedo finally determines what the mean temperature of the surface is. Temperature, however, is not the only condition for a planet to have liquid water. The pressure on its surface must also be taken into account. Planets that are too large will probably have an important, massive atmosphere. And if the atmosphere is too massive, the pressure at the surface will not allow water to be liquid. Conversely, if the planet is too small, it might not be massive enough to retain its atmosphere, which could gradually evaporate into space. This is the case with Mars, which has a very light atmosphere. Although during the Martian day its temperature can be pleasant, around 20 degrees Celsius, the pressure is so light that if water existed on its surface, it would change directly from ice to vapor. So, we need to find planets that have a size approximately between that of Mars and 1.5 times that of the Earth. It is believed that in this mass range, planets have the best possibility of retaining liquid water at their surface. Thousands of millions of years ago, Mars was very similar to our planet. Perhaps it once held life, and below its surface, this life may still exist. Today, we know that some regions of the Earth that were once considered sterile actually contain extremophilic microorganisms capable of living under extreme conditions of temperature, pressure, or acidity. It seems that life is highly adaptable, very tenacious, and even in extreme sites, we find bits of it, a few species hanging on or well adapted to those environments. Are the limits to life much wider than we imagine? If this were the case, our possibilities of finding it would surely increase. 20 years ago, we didn't even know how to find one planet. Now we have found thousands. Now we will be finding Earth-like planets as well, and then we can start looking to see if they are really habitable, and if there is life on them or not. Finding a small, rocky planet like the Earth is, as we've seen, easier if it's near its star. On the other hand, if we want to find life, it is essential for the planet to be in its habitable zone. To ensure that these two requirements, detectability and potential habitability, are met, astronomers must increasingly search for a type of star that is smaller and colder than our sun, the red dwarfs. Anytime you go outside on starry nights and look at the sky, none of the stars that you are seeing with your naked eye is a red dwarf. They are so faint that none of them can be seen without a telescope, and still, they outnumber the stars that you are seeing. Red dwarfs are the most abundant stars in our galaxy. A remarkable 70% of all stars in our galaxy are red dwarfs. And they are very interesting because, with our current techniques and instrumentation, we can learn more things about their planets. and we have a realistic hope of not only detecting the planet, but also looking at what the atmosphere of those planets are made of. They are considered the most suitable candidates to be explored for the presence of life. Red dwarfs also have another crucial advantage: their incredible longevity. Red dwarfs burn their nuclear fuels very, very slowly. So when they sit on the main sequence, which is where stars steadily burn hydrogen in their cores, red dwarfs can be there for the whole of the age of the universe, and much longer. Life, if it arises, has literally all the time in the world to develop. In recent years, planets similar in size to the Earth have indeed been found orbiting within the habitable zones of red dwarf stars. Could any of them provide conditions genuinely suitable for life? This kind of planet is easier to detect, and today we have several candidate planets in the habitable zones of these stars. But we have to keep in mind that these planets, to be warm enough, are so close to their small star that maybe this is not really the better condition for life development. Red dwarfs are much more active than our Sun and could potentially finish off the atmosphere of a nearby planet in a few million years with powerful flares, without giving life time to develop. Moreover, as they are so close to each other, the gravity of the star often captures the rotation of the planet, so that the latter always shows the same face to the star, tidal locking. This causes huge differences in temperature between the hemisphere that receives light and the one in perpetual shade. With such a gloomy outlook, one might ask if planets could develop mechanisms to favor the emergence of life. Further studies and more advanced observations could give us the answer. For centuries, human beings have tried to know if we are alone in the universe or not. At the moment, we have, for the first time probably in our history, started a very challenged program that will dedicate many, many nights on 4-meter class telescopes to make the first survey of Earth-like planets around these red dwarfs. Who knows if maybe in some centuries or so, this survey could be used as a roadmap to go to other places, because in the end, what we are searching for are similar homes to our own. An instrument crucial for implementing this project is Carmenes, which has been installed in the largest telescope in mainland Europe. Jesus Aceituno and his team are searching for planets like the Earth around red dwarf stars. They select a sample of about 300 stars and are monitoring those stars almost every night. What is really new in Carmenes is that it observes simultaneously from the very blue wavelengths all the way until the infrared ones. And this is what converts Carmenes into something really unique in the world. Observation over this wide range helps to differentiate the signal of a planet from that which the activity of a star generates. In addition, Carmenes will also allow scientists to find out the composition of the atmospheres of these planets. With Carmenes, they have the technology to know the chemical composition of the atmosphere, which is also the second important part, just to be sure there could actually exist life on the surface of the planet. Atmospheric whispers, giant eyes, and the enduring dream. The study of the components of atmospheres on distant planets is a major challenge, a frontier in which we are still taking the very first tentative steps. Right now, we have discovered thousands of these exoplanets. Now, we would like to characterize them. We would like to know more about them than just the fact that they exist. There is a lot of experimental work being built, a lot of sophisticated instruments being developed, all with the aim of trying to access these precious atmospheric data. It's not easy. It's actually much easier to detect a planet now. although it wasn't easy at all at the very beginning. But now we generally know how to do it. So detection is no longer the primary problem for many types of planets. But it's much more difficult to go now and actually measure things at the surface, or more realistically, in the atmosphere of these distant worlds. And the only thing we can really measure from so far away, across light years of intervening space, is the planet's atmosphere. We are now in the era of detecting potentially habitable planets, particularly around these small red dwarf stars. But in doing so, we are also diligently preparing for the real, ultimate detection of other Earths, meaning Earth-type planets orbiting stars very much like our Sun. And that capability, astronomers anticipate, will likely come within the next 10 to 15 years. And hopefully, by then, we will also have the new, even more powerful facilities needed to then effectively characterize their atmospheres. Because that's another enormous challenge, perhaps the greatest of them all. Discoveries such as the remarkable TRAPPIST-1 system, a nearby ultra-cool dwarf star orbited by 7 Earth-sized planets, several of which lie within its habitable zone, and all of which transit their star as seen from Earth, provide excellent, almost tailor-made opportunities for studying atmospheres. When there is a transit, the planet passes directly in between its star and us, the observers. So, some of the starlight will filter through the upper layers of the planet's atmosphere, if it possesses one, before that light continues its journey to our telescopes and detectors. Consequently, superimposed upon the light spectrum of the star, there will be a faint, subtle imprint, a spectral signature, of the chemical composition of the planet's atmosphere. If you can accurately measure this tiny variation in starlight at different wavelengths, a technique known as transmission spectroscopy, you have a direct method to access information about the atmospheric constituents and potentially even find traces of life. How, then, can we identify these elusive traces of life, these biosignatures, from such immense distances which specific elements, or more likely, combinations of elements, present in a distant planet's atmosphere must appear for us to even begin to suppose, with any degree of scientific confidence, that they are inhabited, if a hypothetical alien observer were looking at our own planet, Earth, from a very far away vantage point, and possessed the sophisticated technology to analyze our atmosphere, they would be able to see certain distinct atmospheric signals. They would certainly detect the presence of abundant water vapor. They would also see significant quantities of oxygen, a highly reactive gas that, on Earth, is overwhelmingly produced by photosynthetic life. And they would likely find other gases, such as methane and carbon dioxide, in concentrations that are also influenced by biological processes. The detection of these 4 elements, water, oxygen, methane, and CO2, all coexisting in significant quantities within the same planetary atmosphere, is something that would be very strange from a purely non-biological chemical perspective, because some of these gases, like oxygen and methane, tend to react with each other and destroy each other over geological timescales. Their sustained coexistence implies that there is a powerful, continuously operating system that is producing and replenishing them, a system that, on our planet, is life itself. Finding planets that are more and more similar to the Earth, and then meticulously studying their atmospheres in a dedicated search for these crucial biomarkers, are key objectives in the ambitious missions that will be developed and launched by the major space agencies in the forthcoming years. With its magnificent mirror of 6.5 meters, the new James Webb Space Telescope is already demonstrating its power, about 100 times more potent than the Hubble Space Telescope in its light-gathering ability and infrared sensitivity. There has never been a telescope of these dimensions, optimized for infrared observation, placed in space before, which means that what it discovers, the new views of the cosmos it is providing, could fundamentally change our entire concept of the universe. Astronomers were waiting for the James Webb Space Telescope for many years, and it is proving to be our ideal machine to learn much more about exoplanets. And what's the reason for this? This telescope is the most sensitive instrument ever deployed in space to capture infrared light. For the study of exoplanets, we can actually do two crucial things with it. We can attempt to image some of the planets we already know, particularly larger, younger ones, and we can measure their spectra, allowing us to derive the chemical composition of their atmospheres. The European Space Agency also has its own dedicated telescopes in operation or advanced stages of planning. Cheops, for instance, is tasked with the mission of studying exoplanets that have already been discovered, refining our knowledge of their properties. As Willie Benz, the principal investigator of the Cheops telescope, aptly stated, "If you look for life, if you look for something, the first thing you need to know is where to look." Right. You need to know where to look, and therefore you want to have a list of objects which optimize your chances. So as you think to find what you're looking for, looking ahead, 2026 is a key date. In that year, the European Space Agency plans to launch the Plato mission. Michel Mayor and Stefan Udry, pioneers in the search for exoplanets, believe that Plato will be essential if we are to find a true twin planet for the Earth. Plato will have 24 cameras, which will analyze the light curves of over 200,000 stars in search of planetary transits. It will look at many stars at the same time, especially bright stars, across a great part of the sky, trying to look really for planets like the Earth orbiting stars that look like the Sun. Many of the planets that these space telescopes will discover in the forthcoming years must then be confirmed and further characterized from Earth, often using the radial velocity method to determine their masses. The effect of the Earth on the Sun, changing the velocity of the Sun, is a minuscule 9 centimeters per second. Achieving this level of precision is a new step forward in instrumental improvement. This new step is already in motion. At the Geneva Observatory, a spectrograph 10 times more powerful than previous ones, named Espresso, has been built and installed on the Very Large Telescope in Chile. The goal of this new project is to achieve a precision of 0.1 meters per second, or 10 centimeters per second. And this just opens the possibility to detect these kinds of planets, like the Earth, orbiting a star like the Sun. This effect is so small when it's due to small planets that astronomers have to build incredibly dedicated instruments, often putting them in a vacuum to eliminate changes of temperature or pressure, because a change of 1/100th of a degree or 1/100th of a millibar in pressure will already induce an effect that is 10 times bigger than the effect of the Earth on the Sun. So, scientists really have to push to the absolute limit the technology of these spectrographs. However, the greatest technological challenge that scientists are currently facing in ground-based astronomy is taking shape in the high desert of Chile. It is there, at the European Southern Observatory that a truly revolutionary instrument is being built, the Extremely Large Telescope, or ELT. In a few words, the ELT is going to be the biggest highway towards a new understanding of our universe. It will give us the opportunity to discover things that today we cannot even imagine. When its construction is completed, anticipated around 2024 or 2025, it will be the largest telescope in the world, with a primary mirror an astounding 39 meters in diameter. The ELT will gather up to 15 times more light than current large telescopes and will be able to distinguish objects with a resolution never previously achieved. Think about a big spotlight beam in a soccer field and put just 10 centimeters away from it a little LED light. The ELT aims to distinguish, to resolve, the light of this tiny LED from the glare of the big spotlight, but from a distance of 200 kilometers away. The true potential of the ELT will be its capacity for capturing images of exoplanets orbiting nearby stars. Now, it won't be an image in the sense that you will see continents and water and clouds. What we'll see is a point source of light. But by looking and actually seeing that point source directly, it gives us the possibility to take the light from that point source and split it up into its component rainbow colors. And if we can find evidence for molecules in the atmospheres of those planets, such as ozone and methane, then we will definitely be able to show, unequivocally, that life exists on those planets. The universe that we discover with the ELT may cause in us the same profound astonishment that Galileo felt when he looked through his simple telescope for the first time. If you look back at how our understanding of the universe has changed in just the last 30 years, it's hard to imagine how much more of an understanding we'll have in another 30 years. But many are confident that in that time frame, we will have characterized planets around other stars, and we will have found the evidence that life actually exists around those other stars. What we are learning in science, historically, is that when you discover something, it's often opening more questions, and we are facing more surprises than anticipated. The first planets that were detected were Jupiters very close to their stars, and we know that they cannot form there. Super-Earths don't exist in our solar system, so we had no idea that they could be so numerous. There is a huge diversity. So, that's for the habitat for the development of life. Among all this diversity and abundance of planets, shall we find another place like Earth where life has been able to arise? Personally, many scientists are very favorable to the idea that life, at least in microorganism form, exists on other planets with convenient conditions. But this is not science. The only way is to do measurements and to detect this kind of form of life. It will not be so easy to prove 100% sure that a planet has life on it. It will be kind of hard because you want traces that are only due to life and not due to natural phenomena. And this is hard. There are a lot of things we can imagine that are also produced by natural phenomena, and we will have to be sure to disentangle these. The feeling is that we will have to have several lines of evidence, not just one, because it is a big claim to make. On our planet, chemistry evolved for thousands of millions of years to form intelligent life, beings aware of themselves who consider their place in the universe and look for answers. If life is very common, then we will find it very soon because it's everywhere. If life is rare in the universe, then it will take a long time to find, because we will need to find the right planet to look at. And if life doesn't exist anywhere else in the universe, then we'll never really know, because not finding it will not be proof that it doesn't exist. Whether we are successful or not, the search for another Genesis, for another instance of life beyond the limits of our solar system, will have been worthwhile. If we do believe that there is a kind of a mandatory evolution towards the development of life, then it should be everywhere. But of course, there's a competition between what we call convergence, the idea that because the laws of chemistry and physics are the same everywhere, the same evolution should take place. But there are also the contingencies, the random events that will help or destroy life from place to place. So it's a statistical, kind of big, chaotic process. And the outcome will be 0 or 1. Either it's very, very hard to have life, or it's everywhere. And many choose to believe in the everywhere. The search continues, a testament to the enduring human spirit that reaches for the stars, that yearns to understand its place in the vast, silent cosmos. Whether we find echoes of our own existence or confront an even more profound solitude, the journey itself transforms us, deepens our appreciation for the precious, fragile gift of life on this small blue world, and reminds us that in the grand cosmic play, the pursuit of knowledge, the dream of connection, is perhaps what makes us truly alive. The universe waits, patient and profound, and we, its curious children, continue to listen for its secrets, for the whispers of other worlds, for a reply to our oldest question.
Of all the questions we can ask about existence, perhaps the most profound is also the most unsettling. Why is there something rather than nothing? Why do you exist? Why does anyone? Why does the world, with all its beauty and brutality, its complexity and contradiction, persist at all? From the molecules in your breath to the vast galaxies spinning silently in the cosmic dark. Why are any of these things here? According to our best understanding of physics, they shouldn't be. The universe itself, its stars, its silence, its laws, and its life should never have been born. To begin unraveling this paradox, we must return to the very first instant, the birth of everything, the Big Bang. It was not merely an explosion of matter, but of space-time itself, a singular event of unimaginable energy and baffling precision. The odds that such an ordered cosmos could emerge from primordial chaos were not simply slim, they were vanishingly small. British physicist Sir Roger Penrose attempted to capture just how improbable this beginning was. His estimate, a number so staggeringly huge it defies intuition, has come to be known as the Penrose number 1 in 10 to the 10 to the 123. That is a 1 followed by more zeros than the number of atoms in the observable universe, a number so extreme that calling it impossible barely does justice to its scale. It speaks to a universe birthed not in chaos, but in breathtaking coherence, like a cosmic sculpture chiseled with infinite precision. This low entropy beginning is deeply mysterious. As time flows forward, systems tend toward disorder. It's the arrow of time. Entropy increases and order decays. We see it in the slow ruin of ancient cities and the fraying of our own bodies in the tangled knots of headphone wires left in a drawer. We expect the same of the cosmos. Black holes, as Penrose noted, are the ultimate endpoints of this decay, the graveyards of structure where complexity collapses into featureless oblivion. Yet here we are, nearly 14 billion years after the beginning, still surrounded by intricate structures, by stars, by minds, by the astonishing dance of life and matter. the universe remains astonishingly ordered. And entropy is not our only puzzle. We live in a world dominated by matter, by the particles that make up you, me, the Earth, and the stars. But every particle of matter has an opposite antimatter. And when matter meets antimatter, they annihilate each other in a flash of pure energy. So, where is all the antimatter? Why did just enough matter survive the primordial inferno to build a cosmos when our equations suggest symmetry should have ruled equal parts matter and antimatter destined to destroy each other completely? Nothing should remain. Not a single atom. And yet, improbably something did. Then, perhaps most baffling of all, comes the issue of weight. Not of stars or galaxies, but of space itself. Quantum theory tells us that even in a perfect vacuum, energy bubbles and boils into existence. These fluctuations give empty space a weight, one that when calculated using our best understanding of quantum fields is staggeringly high. So high, in fact, that the moment the universe sprang into being, it should have curled back in on itself and vanished. It should have been crushed by the weight of its own emptiness. Instead, the universe expanded. Space stretched, light emerged, galaxies formed. The cosmos lived. This vast mismatch between theory and observation is known as the cosmological constant problem, and it haunts modern physics. It is not a subtle discrepancy. It is a chasm between the predictions of our models and the reality we observe. It tells us that something fundamental is missing in our understanding, something hidden deep in the structure of the vacuum itself. And so we are left with a troubling truth. We should not be here. Not because of a failure of imagination, but because of a failure of explanation. The universe is not just improbable, it is by all accounts impossible. And yet impossibly it is here, and so are we. What is energy? At first glance, it seems a straightforward question. Yet, beneath its surface lies one of the most profound concepts in physics, an idea that binds together the functioning of stars, the breath in our lungs, the technology we use, and even the mass of the cosmos itself. Energy is not a single entity, but a unifying thread connecting diverse processes and phenomena, from the combustion of fuel in a locomotive to the fusion of hydrogen in the heart of the sun. But understanding how we came to see it this way requires a journey not through equations, but through observation and insight, beginning with an unlikely figure aboard a 19th century sailing vessel. Julius Robert von Meyer, a ship's doctor sailing through the Dutch East Indies in the 1840s, was struck by an unusual detail. Treating sailors in the tropical heat, he noticed that the color of venous blood, the blood returning to the heart, was brighter than expected. In colder climates, such blood would appear darker, depleted of oxygen after fueling the internal combustion that keeps our bodies warm. But in the suffocating heat of the tropics, the sailors' bodies didn't need to burn as much food for warmth. Their metabolism slowed and less oxygen was consumed. The blood, returning to the heart, was nearly as red as when it left the lungs. This small biological observation led von Meyer to a remarkable conclusion. The energy that the body normally produces through metabolism was being supplemented by the heat of the surrounding environment. In short, heat and biological work were interchangeable. He had glimpsed a universal principle. Energy may take many forms, but it is conserved and convertible. By the mid-19th century, such ideas were beginning to coalesce into a broader framework. Scientists realized that energy could be stored, transferred and transformed, whether in the potential energy of a suspended weight, the chemical bonds of coal, or the expanding steam that powered industrial machinery. Energy, in essence, was capacity. The capacity to do work. And work in physics is the application of a force across a distance. These foundational insights prepared the stage for the 20th century, when energy would be redefined yet again, this time in the most unexpected place, in the very mass of objects. Albert Einstein's theory of special relativity, published in 1905, did more than upend our notions of space and time. It also transformed our understanding of inertia. Imagine a hypothetical scenario where an idealized human, a supercharged Usain Bolt, could be accelerated to near the speed of light. To push him faster and faster, more energy would need to be fed into the system. Yet, as his velocity approached the universal limit, his resistance to further acceleration would increase. This resistance is not arbitrary. It is inertia. And what Einstein saw was that the energy being added wasn't disappearing. It was manifesting as growing inertia. And inertia is another word for mass. In a moment of sublime clarity, Einstein saw that mass and energy are two expressions of the same fundamental thing. And this insight he captured with his most iconic formula, E equals mc2. The implications of this are profound. It tells us that even at rest, an object contains an immense amount of energy. The c in that equation, the speed of light squared, is a massive multiplier. A modest 9-kilogram object, like a small dog, contains energy equivalent to 200 megatons of TNT. This is not just theory. This mass-to-energy conversion powers nuclear weapons and fusion reactors. In both, mass is transmuted into heat light and kinetic energy. And in the cores of stars, including our Sun, this process sustains the very existence of life on Earth. Hydrogen nuclei fuse into helium, releasing energy as they lose tiny amounts of mass. The difference is minute but multiplied across a star's lifetime. It becomes monumental. Einstein's revelation also changed the way we think about gravity. In Newton's formulation, gravity pulled on mass. But Einstein, having unified mass and energy, realized that gravity must pull on energy as well. Light, though massless, is bent by gravity because it carries energy. This is not a metaphor. It is a measurable, observable phenomenon. Light from distant stars is deflected as it passes near massive bodies, an effect confirmed during the solar eclipse of 1919 and now seen routinely in the lensing of galaxies. So when physicists ask how much something weighs, they are not concerned solely with its mass. They are asking about its total energy content. This includes not just the rest mass of the object, but also its kinetic energy, its internal energy, and even the energy contained in the space around it. The universe therefore has a weight, and that weight is determined not only by the visible matter star's gas dust, but also by radiation kinetic motion, and most mysteriously the vacuum itself. This brings us to the heart of modern cosmology. The mass-energy content of the universe is the source of its gravitational behavior, and when we survey the cosmos, we see a surprising pattern. The visible matter accounts for a mere fraction of the total energy budget, roughly 5%. Dark matter, an unseen but gravitationally active substance, accounts for another 25%. The remaining 70% is something stranger still: dark energy, an invisible component permeating empty space and driving the accelerated expansion of the universe. This is where the concept of energy becomes most enigmatic. The vacuum, seemingly empty, is not truly void. Quantum field theory tells us that even in the absence of particles, energy remains. Virtual particles pop in and out of existence, borrowing energy on short timescales in accordance with the uncertainty principle. But this vacuum energy carries weight, and gravity responds to it. The cosmological constant, Einstein's term for the energy density of the vacuum, exerts a repulsive force, causing space itself to expand. When physicists attempt to calculate this vacuum energy using quantum theory, they arrive at a catastrophic number, many orders of magnitude higher than what is observed. The difference between theory and reality is one of the greatest in all of science. This is the cosmological constant problem. The energy of the vacuum should be so immense that the universe would have torn itself apart at birth, and yet it did not. Something is missing in our understanding, some piece of the puzzle not yet found. So, what is energy? It is heat and light motion and mass radiation and gravity. It powers stars and sustains life, and it defines the weight of the universe itself. From the biological insight of a 19th century physician to the relativistic revolutions of the 20th century, our conception of energy has evolved into something profound and mysterious. As we turn our instruments to the skies and attempt to weigh the cosmos, we are not just measuring mass. We are measuring the energy of everything, the visible, the invisible, and perhaps the unknowable. How much does the universe weigh? In the 3rd century BCE, in the city of Syracuse, the great mathematician Archimedes turned his mind toward a question that, though deceptively simple in phrasing, demands the loftiest intellectual tools to address how many grains of sand could fit inside the cosmos. In his treatise, known as the Sand Reckoner, Archimedes dismissed the notion that the quantity of sand in the universe was infinite, and instead set out to calculate a number one anchored in tangible, measurable quantities, beginning with the width of a poppy seed and extrapolating to the entire celestial sphere. This endeavor led him to construct an entirely new numerical system, and by estimating the universe to be a sphere centered on the sun and bounded by the fixed stars, he concluded that it would contain no more than 163 grains of sand. The estimate, astonishingly close to modern conceptions of the universe's mass-energy content, was of course a numerical coincidence, since Archimedes was constrained by the astronomical knowledge of his day. Nonetheless, his desire to quantify the cosmos laid conceptual groundwork that resonates even now. Today, we no longer speak in terms of poppy seeds and grains of sand, but in terms of energy mass, space-time curvature, and quantum fields. When cosmologists ask how much the universe weighs, they are not weighing celestial bodies with scales, nor are they tallying particles one by one. Instead, they are evaluating how much total energy exists within the observable universe, and how that energy in all its various forms distorts the fabric of space-time. This, in essence, is the weight of the universe, not a weight in the Newtonian sense, but a measure of the energy content that governs the gravitational dynamics of the cosmos. To estimate such a quantity, one must first delineate what is meant by the universe. More precisely, scientists focus on the observable universe, that portion of the cosmos from which light has had time to reach us since the Big Bang, roughly 138 billion years ago. One might initially suppose that this corresponds to a sphere 138 billion light-years in radius, but that would be an oversimplification. Due to the expansion of space over cosmic time, the most distant galaxies we can observe today are actually around 465 billion light-years away. This defines the radius of our observable universe, making its diameter nearly 93 billion light-years. This sphere encompasses all that we can potentially observe, but not necessarily all that exists. Beyond its horizon may lie further galaxies, further structures, perhaps even regions governed by different laws of physics. We simply do not and cannot know. For our purposes, however, we restrict ourselves to the observable universe, and within that finite yet vast domain, we attempt to sum up the total energy content. We begin with stars. The Sun. An average-sized star has a mass of approximately 2 × 1030 kilograms. The Milky Way galaxy contains an estimated 100 to 400 billion stars, amounting to a stellar mass of about 1042 kilograms. There are at least 200 billion galaxies in the observable universe, each containing roughly 100 billion stars, suggesting the total stellar mass is approximately 2 cos 1052 kilograms. This is already an enormous figure, but it accounts only for the luminous material stars and perhaps planets and visible interstellar gas. However, much of the universe's matter is not luminous. A more precise measurement comes from analyzing the effects of matter and energy on the geometry of the universe itself. One of the most powerful tools for doing so is the study of the cosmic microwave background radiation, or CMB, the afterglow of the Big Bang, now cooled to just 27 Kelvin. This ancient radiation carries with it the imprints of the universe's earliest fluctuations in temperature and density fluctuations that seeded the formation of galaxies and large-scale structure. Using data from satellites such as COBE, WMAP, and Planck, cosmologists have measured minute temperature variations in the CMB across the sky, and from the statistical properties of these variations inferred the density and composition of the universe with remarkable precision. From these measurements, we now estimate the total mass-energy content of the observable universe to be approximately 15 Gotsa 1053 kilograms. This includes not only the visible stars and gas, but also all matter, baryonic and non-baryonic, and radiation. And when we convert this mass into energy using Einstein's famous relation E equals mc2, we find the equivalent of about 135 size 70 joules of energy. It is an incomprehensibly vast reservoir, yet it represents only a small fraction of what the universe actually contains. That is because the visible matter, the atoms that compose stars, planets, and people, accounts for only about 5% of the universe's total energy content. The rest is composed of two enigmatic components, dark matter and dark energy. Dark matter is a form of matter that does not emit, absorb, or reflect light. It interacts gravitationally but not electromagnetically, making it invisible to our instruments. Its existence is inferred from its gravitational effects on the rotation of galaxies, the dynamics of galaxy clusters, and the bending of light from distant sources via gravitational lensing. Dark matter comprises about 27% of the universe's energy budget. Yet, even dark matter is not the dominant component. That distinction belongs to dark energy, an even more mysterious substance that constitutes roughly 68% of the total. Unlike dark matter, which pulls structures together through gravity, dark energy is responsible for the accelerated expansion of the universe. Its effects were first observed in the 1990s through studies of distant type Ia supernovae, which appeared dimmer than expected, suggesting that the rate of cosmic expansion had increased rather than slowed over time. Dark energy behaves differently from all other forms of matter and radiation. It has an energy density that remains constant as the universe expands. This is deeply counterintuitive. Ordinary matter becomes more dilute as the universe stretches. So does radiation, whose energy per photon also diminishes, but dark energy remains the same per unit volume. This implies that as space expands, new dark energy is created, a bizarre but consistent consequence of general relativity when applied to a vacuum with energy. This vacuum energy, referred to variously as the cosmological constant, the zero-point energy, or the vacuum expectation value, permeates all of space. Quantum field theory tells us that even in a perfect vacuum where no particles exist, quantum fields are never truly at rest. They fluctuate constantly, creating short-lived virtual particles that emerge and vanish in a seething quantum froth. These fluctuations contribute energy to empty space, and that energy gravitates. It bends space-time just like mass does. This vacuum energy, according to quantum theory, should be enormous. So enormous, in fact, that it would have curved the universe into oblivion in a fraction of a second after the Big Bang. This brings us to one of the most profound problems in modern theoretical physics, the cosmological constant problem. The discrepancy between the predicted and observed values of the vacuum energy is not merely large, it is the largest known disagreement between theory and observation in all of science. Quantum field theory predicts a vacuum energy density that is 120 times greater than the observed value. This is a number so large that it defies imagination. It suggests that if the vacuum energy were truly as predicted, the universe would have imploded almost immediately after its creation. No stars, no galaxies, no structure, certainly no life would ever have formed. And yet, here we are. The vacuum. Energy, for reasons no theory currently explains, is small. Astonishingly small, yet non-zero. It is precisely the right magnitude to allow for a universe that grows slowly over billions of years. A universe that permits the emergence of complexity biology and consciousness. This apparent fine-tuning of the cosmological constant remains one of the greatest mysteries in cosmology. It suggests either an underlying principle yet to be discovered, or perhaps a selection effect in a multiverse scenario where many universes exist, each with different vacuum energies, and we find ourselves in one of the rare few where conditions are right for life to emerge. In total, when dark energy is included, the full energy of the observable universe converted into the TNT equivalent to illustrate its staggering scale amounts to approximately 67 × 10^54 kilograms of mass energy, or roughly 60 × 10^71 joules. But this energy, vast as it is spread thinly across the immense volume of space. The average energy density of the universe is incredibly low, less than a few hydrogen atoms per cubic meter, and dark energy even more diffuse. A coffee cup filled with vacuum energy contains less energy than the kinetic energy of a falling mosquito. It is only because space is so vast that these small quantities add up to such a significant gravitational influence. And so, in the final reckoning, our universe is not massive because it is densely packed with material, but because it is so vast. Its weight in the sense of total energy emerges from the product of low density and enormous volume. And within that volume lies not only all the matter and energy we can see, but all the structure that makes up the cosmos, from stars and galaxies to clusters and filaments emerging and evolving under the inexorable influence of gravity. To weigh the universe, then, is not merely to count stars or some particles. It is to measure the full story of cosmic energy in all its forms, to understand how the vacuum itself contributes to the architecture of the cosmos, and to confront the greatest mysteries that theoretical physics has yet to solve. Why does the vacuum weigh so little? Why is the cosmological constant not immense? And what principle of nature carved such an exquisitely balanced universe, one vast enough to grow old, stable enough to form galaxies, and gentle enough to allow us to ask at last just how much it weighs? The nullpunkt's energy. What is the true nature of empty space? Could the vacuum itself, seemingly so inert, so devoid of structure, conceal an energy so immense it challenges the very survival of the universe? To begin unraveling this mystery, we must return to a moment nearly a century ago, to the vibrant city of Hamburg, a beacon of intellect and science in post-war Germany. There, in a modest cafe overlooking the tranquil waters of the inner Ulster, two physicists, friends, and colleagues shared a conversation that in hindsight stood at the precipice of one of the greatest cosmological enigmas of our age. Otto Stern, a cultured man with a passion for good wine and better company, leaned in to make his case. He was animated, brandy in hand, eyes bright with conviction. His friend across the table, Wolfgang Pauli, bore a fading black eye, the remnants of a barroom scuffle in Hamburg's raucous St. Pauli district. though their temperaments diverged. Stern, the affable bon vivant Pauli, the volatile iconoclast, they were united in their pursuit of physics at its most fundamental. That day, they debated a concept now known to us as the vacuum energy, or, in German, the Nullpunktsenergie, the zero-point energy. Stern argued from observation, invoking data from the vapor pressures of neon isotopes. The discrepancy he calculated could not be reconciled without invoking the subtle presence of this ever-present energy, lurking even in the absence of matter. Pauli, characteristically skeptical, countered with a stark warning. If the Nullpunktsenergie truly existed in the quantity that quantum theory implied, it would have profound gravitational consequences. The universe, he claimed, wouldn't extend beyond the distance from Earth to the Moon. It would collapse upon itself under the weight of its own vacuum. This disagreement, passionate, personal, and profound, marked one of the earliest acknowledgments of a paradox that continues to confound physicists to this day. The idea that empty space might contain energy wasn't new. As early as 1911, Max Planck had speculated about zero-point fluctuations, suggesting that even in the absence of all matter and heat, a residual energy might remain. A few years later, Walter Nernst took the bold step of proposing that this energy might pervade all of space, an all-pervasive invisible sea of latent potential. Yet it was Albert Einstein who introduced a separate but ultimately related concept, the cosmological constant, a term added to his general theory of relativity in 1917 to balance the gravitational pull of matter and achieve a static universe. Einstein's relationship with these ideas was complicated. Initially, he supported the cosmological constant as a mathematical necessity. He even collaborated with Stern to estimate the impact of zero-point energy on hydrogen molecules, but he failed to connect the two concepts, as observations revealed that the universe was not static but expanding. Einstein famously recanted his cosmological constant, referring to it allegedly as his biggest blunder. Likewise, he distanced himself from zero-point energy, deriding its mention with a self-deprecating smirk. But time would show that both the constant and the vacuum energy were far more than mathematical curiosities. They were central to the workings of our universe. The turning point came in the 1920s as quantum mechanics rose from the mathematical mist. On the island of Helgoland, beset by allergies and insomnia, Werner Heisenberg wrestled with the spectral lines of hydrogen atoms. There, amidst the dunes and salty air, he formulated what would become the uncertainty principle, an insight into the intrinsic unpredictability of nature at the smallest scales. Heisenberg's principle asserted that certain pairs of physical properties like position and momentum could not be simultaneously known with arbitrary precision, and from this the idea of zero-point energy naturally followed. If a particle could never be precisely at rest, then even in its lowest energy state it must possess some residual motion, some irreducible energy. To visualize this, imagine placing a marble in the bottom of a smooth bowl. In the classical view, it settles motionless at the lowest point, its energy fully expended. But in the quantum world, such rest is forbidden. To know its position exactly would require complete ignorance of its momentum. Therefore, even at absolute zero, the marble must jiggle, however faintly. That jitter, imperceptible though it may be, corresponds to a real energy. Now, replace the marble with a subatomic particle and the bowl with a quantum field. What you discover is that the vacuum itself can never be truly still. It writhes with fluctuations, virtual particles forever appearing and vanishing in a foam of probabilistic activity. These aren't particles in the traditional sense. They cannot be touched, weighed, or isolated. They don't leave direct tracks in detectors, but their effects are real. These vacuum fluctuations give rise to measurable forces. The Casimir effect discovered by Dutch physicist Hendrik Casimir is a striking example. When two uncharged metal plates are brought close together in a vacuum, they experience an attractive force not from electromagnetic interactions, but from the change in vacuum energy between them. This force is real enough to be measured. It even plays a role in the ability of geckos to cling to walls through the subtle van der Waals forces that arise from quantum vacuum effects between molecules. So, if vacuum energy is real, and if it can produce measurable forces, how much of it is there? This is where the problem begins. Physicists like Pauli attempted early estimates by partitioning space into tiny boxes. Imagine dividing a coffee cup of vacuum into infinitesimal regions, each allowed to contain virtual particles with energy limited by the uncertainty principle. Using the best resolution of their time, Pauli and his contemporaries imagined a cutoff scale around a femtometer, the approximate size of a proton. Even at this conservative scale, they found a staggering amount of energy in empty space, enough in a single coffee cup to boil away all the oceans of Earth. Fast forward a century, and we have probed much deeper into the quantum realm. With the Large Hadron Collider smashing particles together at near light speed, we can now resolve distances 100,000 times smaller than a proton. If we use these more refined scales in our vacuum energy calculations, the numbers spiral out of control. The energy density becomes so immense that a coffee cup of empty space could vaporize entire planets. Indeed, entire galaxies, again and again. Go further still down to the Planck scale, the smallest scale at which space and time still retain meaning, and the energy becomes truly catastrophic. At this scale, a single coffee cup of vacuum could contain enough energy to obliterate all matter in the observable universe a trillion times over. And yet, paradoxically, we see none of this space, for all its emptiness behaves gently. The expansion of the universe is slow. Measured, delicate galaxies drift apart. Yes, but the very fabric of space is not heaving under the unimaginable weight of vacuum energy. The catastrophic predictions of theory are not reflected in reality. This is the essence of the cosmological constant problem. You see, in general, relativity, gravity, is not a force in the traditional sense. It is geometry. Energy and mass tell space. How to curve in curved space tells matter how to move. All forms of energy contribute to this curvature. Not just matter, but also light radiation and, crucially, vacuum energy. If vacuum energy is indeed as large as quantum field theory predicts, then its gravitational influence should be overwhelming. The curvature it imposes on space-time should be so extreme that the universe would not just collapse, it would never have emerged in the first place. There would have been no stars, no galaxies, no time for atoms to form or life to arise. The cosmos, born a super heavyweight, would have folded in on itself in an instant. But we are here. The universe exists. The observable cosmos stretches 47 billion light-years in every direction. It is filled with stars, planets, life, and the slow unfolding of time. Somehow, the vacuum energy we measure through observations such as the acceleration of cosmic expansion is not large. It is minuscule. It is 120 orders of magnitude smaller than what theory predicts. That discrepancy, a factor of 10^120, is the largest known between theory and observation in all of physics. It is not a minor oversight. It is a yawning chasm, a crisis. So what might resolve this paradox? Some have speculated that there is a mechanism currently unknown that cancels the vacuum energy almost perfectly, leaving just a tiny residual effect. Others have turned to the anthropic principle, arguing that we observe a small cosmological constant because universes with larger values would collapse too quickly for observers like us to evolve. In this view, the multiverse, a landscape of infinite universes, each with its own physical constants, might explain why we find ourselves in a universe so finely tuned for life. And there are those who suggest that we have misunderstood gravity itself. Perhaps general relativity, elegant though it is, fails to account for the true interaction between quantum energy and space-time curvature. Maybe a new theory, a quantum theory of gravity, will one day reveal a hidden structure that tames the vacuum and explains why its energy doesn't wreak havoc on the cosmos. Until then, the nullpunkt's energy remains a mystery, both tantalizing and terrifying. It whispers to us from the vacuum, hinting at hidden depths, inviting us to reconcile the elegance of quantum mechanics with the curvature of the cosmos. It is the silent architect of the cosmological constant problem, and it is a problem that demands our attention, not merely as a matter of scientific curiosity, but as a profound clue to the architecture of reality itself. In the end, what Pauli and Stern debated over their coffee in Hamburg was more than academic. It was a glimpse into the abyss, the recognition that beneath the surface of what we call empty space lies a storm of quantum unrest, a surging sea of possibility whose true weight we still struggle to comprehend. The universe, it seems, is far more fragile and far more finely tuned than we ever dared to imagine. The cosmological constant problem. In the early autumn of 1949, a seemingly innocuous observation from a weather reconnaissance flight would mark a turning point in global history. A filter paper aboard a U.S. weather plane flying its usual route from Japan to Alaska registered an anomalous spike in atmospheric radioactivity. The filter was dispatched to Los Alamos for further analysis. There, the results were decisive. On September 23rd, President Harry Truman publicly confirmed that the Soviet Union had detonated its first atomic bomb. The nuclear arms race had begun. Beneath the shock waves of this geopolitical shift lay another moment of historical significance, perhaps less immediate in its consequence, but far more enduring in its reach. Just south of the explosion site at Semipalatinsk, Kazakhstan, 8 men sheltered in a trench observing the dawn of the Soviet nuclear era. Among them was Yakov Zeldovich, a towering figure in theoretical physics and head of the Soviet Union's nuclear theory division at Arzamas-16. Zeldovich's contributions to his nation's atomic program were immense, and within Soviet scientific circles he was revered. Yet his intellect extended far beyond the confines of weapons development. He was one of the rare physicists who could effortlessly traverse the frontiers of particle physics, general relativity, astrophysics, and cosmology. 2 decades after witnessing that terrifying mushroom cloud, Zeldovich would play a pivotal role in illuminating one of the most profound and unresolved enigmas in modern theoretical physics: the cosmological constant problem. By the late 1960s, the theoretical frameworks of the 20th century had achieved a remarkable level of maturity. Einstein's general theory of relativity had been tested against the precision of astronomical data and emerged victorious. It redefined gravity not as a force, but as the curvature of space-time caused by the presence of energy and momentum. Meanwhile, quantum field theory had become the dominant lens through which physicists viewed the subatomic world, a powerful amalgam of quantum mechanics and special relativity that described particles as excitations of underlying quantum fields. And yet, when Zeldovich brought these 2 towering pillars together, he encountered a contradiction so severe that it threatened the internal consistency of the entire edifice of theoretical physics. Zeldovich recognized that the vacuum of space, far from being a passive void, should be a dynamic and turbulent arena, one populated by incessant fluctuations of quantum fields spawning virtual particles that blinked into and out of existence at unimaginable frequencies. According to quantum field theory, these ephemeral ripples carry energy, but in Einstein's theory, energy in all its forms curves spacetime. Therefore, the vacuum itself should act as a gravitational source. It should bend the very shape of the universe. But if this vacuum energy, the so-called nullpunkts energy or zero-point energy, really existed in the amounts predicted by quantum theory, its gravitational impact would be catastrophic. Zeldovich calculated that the vacuum energy predicted by quantum field theory should curve spacetime so violently that the universe would collapse into a singularity before atoms, stars, or galaxies had a chance to form. In his own words, clarifying the magnitude of the problem would carry tremendous fundamental significance for our understanding of nature. Here was a paradox that placed two of physics' most successful theories in direct conflict. Of course, this tension was not entirely new. Wolfgang Pauli, decades earlier in the 1920s, had pondered the gravitational consequences of vacuum energy. In a famous anecdote from a cafe in Hamburg, Pauli purportedly estimated the gravitational influence of the nullpunkts energy and concluded that a universe endowed with such energy could not even extend as far as the moon. His calculation, more intuitive than precise, was dismissed by some as fanciful. Yet Zeldovich, working with the more refined tools of post-war theoretical physics, reached a similar but far more rigorous conclusion, and he made the scientific community take notice. So, how do we reconcile this prediction with the universe we observe? After all, our universe is vast and ancient. It stretches 93 billion light-years across in every direction, and it has hosted galaxies, stars, planets, and life for over 13 billion years. If quantum field theory insists that empty space contains an immense, even infinite energy density, why hasn't this energy obliterated the cosmos? This is the cosmological constant problem, and it remains one of the most significant open questions in theoretical physics. On one hand, quantum field theory predicts a staggeringly large vacuum energy. On the other hand, observational cosmology, particularly measurements of the accelerating expansion of the universe, tells us that the actual energy density of the vacuum is small, very small. About 120 orders of magnitude smaller than the value predicted by naive calculations from quantum field theory. It is this discrepancy, sometimes described as the worst theoretical prediction in the history of physics, that demands an explanation, and the stakes are enormous. Resolving this conflict would likely require a radical reimagining of the fundamental principles that govern the universe. One school of thought advocates for a purely empirical approach. Ignore the theory, trust the data. If observations tell us that the vacuum energy is small, then so be it. Perhaps quantum field theory, despite its extraordinary success in describing particle physics, is simply inadequate at describing the vacuum structure of the universe. Yet, this route offers little comfort to those searching for a unified theory of nature. It amounts to giving up on our best theoretical tools, just because they yield the wrong answer. Scientists, by their nature, are not content with that. And so the search continues. Theoretical physicists have proposed a wide range of ideas over the past half-century. Some argue that vacuum energy from quantum fields must be counterbalanced by contributions from other, as yet undiscovered sectors of the universe. Perhaps there exists a new field or mechanism that cancels out the enormous contributions predicted by known particles. But for such a cancellation to yield a net energy density as small as what we observe would require a precision of 1 part in 120, a level of fine-tuning that borders on the absurd. It is like balancing the mass of a trillion suns against an equal weight accurate to the mass of a single electron. Others have taken a more radical path. One of the most controversial yet tantalizing ideas involves the multiverse. According to this view, our universe is just one of many, perhaps an infinite number, each with its own physical laws, constants, and vacuum energies. In most of these universes, the vacuum energy is either too large and positive, blowing the cosmos apart before galaxies can form, or too large and negative, collapsing it in a catastrophic big crunch shortly after birth. But in a tiny subset of these universes, the vacuum energy happens to fall within a narrow range compatible with structure formation and eventually life. This is the anthropic argument. We find ourselves in a universe with a small cosmological constant, not because it had to be that way, but because we couldn't exist in a universe where it wasn't. The vacuum. Energy may well be a random parameter drawn from a vast ensemble of possibilities. The string theory landscape, as it is known. Depending on how one counts, this landscape might contain as many as 1/500 or even 10^7,000 possible vacuum states, each with a different value for the cosmological constant. In this picture, the problem is not why the vacuum energy is so small, but rather why it is small enough for us to be here asking the question. This line of reasoning has both defenders and critics. Some physicists, like Nobel laureate Steven Weinberg, have shown that the anthropic approach can make testable predictions. In the late 1990s, Weinberg and his collaborators argued that if dark energy, the observational manifestation of the cosmological constant, constituted less than 60% of the total energy density of the universe, the anthropic explanation would be invalid. But observational data from distant supernovae soon confirmed that dark energy accounts for about 70% of the universe's energy budget, thus passing this predictive hurdle. Still, many theorists are uneasy with anthropic reasoning. They argue that it undermines the predictive power of science. If any observed value can be explained post hoc by appealing to selection effects in an unobservable multiverse, then what becomes of falsifiability, the bedrock of the scientific method? In the meantime, other speculative ideas continue to surface. Concepts such as vacuum energy, sequestering supersymmetric large extra dimensions, or modified theories of gravity offer alternate routes to solving the cosmological constant problem. Yet, none has emerged as a definitive solution. The problem remains stubbornly unsolved. What is clear is that this mystery lies at the heart of our quest to understand the universe. It is a deep wound in the otherwise elegant framework of modern physics. The cosmological constant problem is not merely an error to be corrected. It is a signpost pointing toward a more profound theory, a missing piece of the cosmic puzzle. It is deeply ironic that the substance causing us so much confusion is nothing at all empty space, or rather what we once thought was empty. We now know the vacuum is anything but empty. It is a seething, energetic ocean, bubbling with virtual particles and quantum fluctuations, and yet its energy density is almost imperceptible, so small that a coffee cup of vacuum holds less energy than it takes to swat a fly. So small that it has allowed the universe to expand slowly, to grow old, to form galaxies, stars, planets, and ultimately life. And so, we return to where we began. We set out to weigh the universe. We measured the masses of stars and galaxies, the halos of invisible dark matter, and the faint glow of the cosmic microwave background. We measured the vacuum itself. And what we found was not a crushing burden, but a delicate balance, a cosmos surprisingly light, improbably gentle, a universe that should not have existed and yet does. And so, the question remains, why is the vacuum energy so small? Why hasn't the universe been destroyed by the weight of its own empty space? What is the true nature of the nullpunk's energy? These are not just questions for physicists. They are questions about existence itself, about why the universe looks the way it does, about why we are here at all.